Tonight we're exploring something that happens constantly, all around you, without your knowledge. Right now, as you sit here, invisible signals from across the universe are passing through your body. Some of these signals have traveled for billions of years just to reach Earth. They've crossed distances so vast that the light leaving their sources began its journey before our planet even existed. Most of these signals are natural, produced by the violent deaths of stars, the spinning of exotic stellar corpses, and the explosive birth of the universe itself. But a few of these signals have never been explained. Scientists have detected patterns that shouldn't exist, repeating bursts from impossible distances, and one signal so strange that the astronomer who discovered it could only scrawl a single word in the margin of his printout. That word was wow. Before we begin this journey through the strangest signals ever received from space, if this kind of exploration interests you, consider subscribing to join future investigations into the cosmos. Now, let's discover how scientists learned to hear the universe and what those cosmic whispers have revealed. For most of human history, we experienced the universe through a single sense. We could see it. The stars above were points of light, unchanging and eternal as far as anyone knew. The ancients mapped constellations and tracked the movements of planets, but they were limited to what their eyes could perceive. Even when Galileo first turned his telescope toward the heavens in 1609, he was still collecting the same visible light that human eyes had always seen. He was simply gathering more of it. For over 3 centuries after Galileo, astronomy remained the science of visible light. We built bigger telescopes with larger mirrors and more powerful lenses, but we were still fundamentally blind to most of what the universe was doing. The cosmos, it turns out, doesn't communicate primarily in visible light. It broadcasts across the entire electromagnetic spectrum, from radio waves longer than football fields to gamma rays with wavelengths smaller than atomic nuclei. Visible light represents a tiny sliver of this cosmic conversation. For all those centuries, we were like people trying to understand an orchestra while hearing only the piccolo. The transformation began in 1932, not through any deliberate attempt to hear the universe, but through an engineer trying to solve a practical problem. Carl Jansky worked for Bell Telephone Laboratories in New Jersey, investigating sources of static that interfered with transatlantic radio communications. He built a rotating antenna array mounted on wheels from a Model T Ford, allowing it to spin and determine which direction interference was coming from. The antenna was about 100 feet across and looked more like a farm implement than a scientific instrument. Jansky methodically catalogued the sources of static. He found interference from nearby thunderstorms and distant thunderstorms. But one source of static puzzled him. It was a persistent hiss that seemed to come from no particular terrestrial source. As he tracked this mysterious static over months of observation, he noticed something remarkable. The hiss peaked at the same time each day, but that time shifted slowly, about 4 minutes earlier each day. This is the key observation that changed everything. 4 minutes earlier each day is the signature of something moving with the stars, not with the sun. The Earth rotates once every 24 hours relative to the sun, but relative to the distant stars, it rotates once every 23 hours and 56 minutes. That 4-minute difference meant Jansky's mysterious static was coming from space itself. By 1933, Jansky had pinpointed the source. The strongest static came from the direction of the constellation Sagittarius, toward the center of the Milky Way galaxy. The universe was broadcasting radio waves, and we had accidentally tuned in. Jansky published his findings, and the New York Times ran a front-page story about the discovery. The headline announced that radio waves had been detected from the center of the galaxy. Yet the scientific community largely ignored this revolutionary discovery. Jansky wanted to build a larger antenna to study the cosmic radio waves in detail, but Bell Labs refused. They had hired him to solve a practical problem, and he had solved it. The static from space wasn't interfering with communications in any significant way. There was no commercial reason to pursue the discovery further. Jansky moved on to other projects and never returned to radio astronomy. He died in 1950 at the age of 44, having opened a door that others would walk through. The person who walked through that door was not a professional astronomer, but a radio engineer and amateur astronomy enthusiast named Grote Reber. Working in his backyard in Wheaton, Illinois, Reber built the first true radio telescope in 1937. He constructed a parabolic dish 31 feet in diameter, entirely at his own expense, using sheet metal and 2x4s. His neighbors thought he was building a monument to his own eccentricity. Reber spent years systematically mapping the radio sky, working mostly at night to avoid interference from automobile ignition systems. He discovered that different regions of the sky emitted radio waves at different intensities. Some of the brightest radio sources didn't correspond to any visible stars. The universe in radio light looked completely different from the universe in visible light. Reber published the first radio maps of the sky in 1944, and slowly the astronomical community began to take notice. After World War II, radar technology developed during the conflict became available for peaceful purposes. Physicists who had spent the war building radar systems turned their skills toward the cosmos. Radio astronomy finally became a legitimate scientific discipline. The early radio astronomers quickly discovered that the universe was far stranger than anyone had imagined. In the 1950s, they began detecting radio sources that seemed to coincide with faint blue stars. These sources were dubbed quasi-stellar radio sources, or quasars for short. When astronomers examined the light from these objects, they found something disturbing. The spectral lines were shifted toward the red end of the spectrum by enormous amounts. If this red shift was caused by the expansion of the universe, as Edwin Hubble had shown happens with distant galaxies, then these quasars were incredibly far away. Some appeared to be billions of light-years distant. But here was the problem. At such distances, for these objects to appear as bright as they did, they would need to be producing more energy than entire galaxies containing hundreds of billions of stars. Yet the quasars varied in brightness over periods of days or weeks. This meant the energy source had to be small, because an object cannot vary faster than light can travel across it. How could something smaller than our solar system outshine a galaxy? The answer turned out to be supermassive black holes. Matter falling toward a black hole forms a swirling accretion disk that heats up to millions of degrees and radiates intensely before crossing the event horizon. Quasars are the blazing cores of distant galaxies where supermassive black holes are actively feeding. We had discovered the most luminous objects in the universe, visible across billions of light years, by listening to radio waves. The strange signals had revealed something unprecedented. This established a pattern that would repeat throughout the history of radio astronomy. A strange signal is detected that seems to violate known physics. Scientists investigate, propose hypotheses, gather more data. Eventually, a natural explanation emerges. But that explanation requires something exotic that we didn't know existed. The universe keeps finding new ways to surprise us. In 1964, two more Bell Labs engineers stumbled onto another strange signal that would reshape our understanding of the cosmos. Arno Penzias and Robert Wilson were using a horn antenna in Holmdel, New Jersey, to test microwave equipment for satellite communications. Like Jansky 3 decades earlier, they encountered mysterious static they couldn't eliminate. The noise came equally from all directions. It didn't vary with time of day or season. They pointed the antenna at New York City, but the noise didn't increase. They pointed it at empty sky, and the noise remained. They checked every component of their system. They found a pair of pigeons nesting inside the antenna and evicted them. They cleaned what Penzias later delicately called a white dielectric material that the pigeons had deposited on the antenna surfaces. The noise persisted. The temperature of this cosmic static was about 3 degrees above absolute zero, corresponding to microwave radiation that seemed to permeate all of space. Meanwhile, just 40 miles away at Princeton University, physicist Robert Dicker and his colleagues were building a detector specifically designed to look for exactly this kind of radiation. They had calculated that if the Big Bang theory was correct, the universe should still be filled with the afterglow of that primordial fireball. The early universe was incredibly hot and dense, filled with plasma that glowed intensely. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form and light to travel freely. That light has been traveling ever since, stretched by the expansion of space from visible light to microwave wavelengths. Dicker's team was preparing to search for this cosmic microwave background when they received a phone call from Penzias and Wilson. The Bell Lab's engineers had found what the Princeton physicists were looking for. The persistent noise was the oldest light in the universe, an echo of creation itself traveling for over 13 billion years before reaching their antenna. Penzias and Wilson won the Nobel Prize in Physics for this accidental discovery in 1978. They had detected the birth cry of the universe, captured as a faint whisper of microwaves filling all of space. The cosmic microwave background taught astronomers that strange signals often turn out to be messages from the most fundamental events in cosmic history. The universe had been broadcasting its autobiography in radio waves. We just needed to learn how to listen. But while the cosmic microwave background was eventually explained, other signals would prove far more mysterious. Some would take decades to understand. One has never been explained at all. The tools were ready, the ears were listening, and the universe was about to deliver signals that would challenge everything we thought we knew. The first of these strange whispers came from a graduate student sifting through miles of chart recorder paper, looking for patterns in the cosmic static. What she found would initially be given a name that hinted at the extraordinary possibility that we were not alone in the universe. The signal was labeled LGM-1, where LGM stood for Little Green Men. The story of that discovery, and the even stranger signals that followed, begins with understanding just how unexpected the universe can be when you're paying close attention. The progression from Jansky's accidental discovery to the cosmic microwave background took only about 30 years, but in that time, our perception of the universe completely transformed. We went from a cosmos that could only be seen to one that could be heard, felt, and measured across dozens of octaves of the electromagnetic spectrum. Each new wavelength revealed phenomena invisible to other senses. X-ray telescopes would later show us the violent hearts of galaxies and the remains of stellar explosions. Infrared telescopes would peer through dust clouds to witness stars being born. Gamma-ray observatories would detect the most energetic events in the universe. But radio astronomy remained special because radio waves penetrate dust and gas that block other wavelengths. Radio telescopes can see across the entire galaxy and beyond, detecting signals from objects hidden from optical view. This made radio astronomy the natural choice for one of humanity's most ambitious endeavors, the search for signals that might be artificial. If other civilizations existed somewhere in the galaxy, they might use radio waves to communicate, just as we do. And if they were broadcasting, our new ears might be able to hear them. The stage was set for discoveries that would blur the line between natural phenomena and the tantalizing possibility of extraterrestrial intelligence. The year was 1967, and a young graduate student named Jocelyn Bell was about to make one of the most important discoveries in the history of astronomy. She was working at the Mullard Radio Astronomy Observatory in Cambridge, England, helping her thesis advisor, Anthony Hewish, study a phenomenon called interplanetary scintillation. The basic idea was straightforward. Radio waves from distant sources twinkle as they pass through the solar wind, the stream of charged particles flowing outward from the sun. By studying this twinkling, astronomers could learn about both the solar wind and the distant radio sources themselves. To conduct this research, Bell and Hewish had constructed an enormous radio telescope consisting of over 1,000 wooden posts connected by more than 120 miles of wire and cable. The telescope covered an area of about 4 acres, roughly the size of 57 tennis courts. It looked less like a scientific instrument and more like a field of oversized clotheslines. But it was extraordinarily sensitive to the kind of rapid fluctuations they were trying to detect. Bell's job was to analyze the output from this telescope, which was recorded on rolls of chart paper that scrolled continuously from the recorder. Every few days, she would have nearly 100 feet of paper covered with squiggly lines representing the radio intensity from different parts of the sky. She learned to recognize different types of signals. Interference from Earth-based sources had certain characteristics. The scintillation they were studying had others. But in August 1967, she noticed something that fit neither category. It was what she later described as a bit of scruff, a quarter-inch of unusual marks on the chart paper that didn't look like interference or scintillation. Most people would have ignored it. The marks were tiny compared to the reams of normal data, but Bell had developed an instinct for anomalies. She had been reviewing so much data for so many months that she had become sensitive to anything that didn't fit the expected patterns. She marked the scruff and continued her work. When she went back to examine that section of sky more carefully, the scruff appeared again at the same celestial position. This was significant. Terrestrial interference doesn't return to the same point in the sky because the sky appears to move as Earth rotates. Whatever was causing the scruff was moving with the stars. It was genuinely out there, somewhere in space. Bell brought the anomaly to Hewish's attention, and they began investigating more seriously. Using faster chart recorders that could capture more detail, they discovered something astonishing. The scruff wasn't random noise. It consisted of pulses arriving with clockwork regularity, one pulse every 1.337 seconds. The precision was remarkable. Whatever was producing these pulses was keeping time more accurately than any mechanical clock on Earth. Natural objects weren't supposed to do this. Stars don't pulse with such precise regularity. No known astronomical phenomenon could explain a cosmic metronome ticking away in the depths of space. The Cambridge team was faced with a disturbing possibility. What if the signal was artificial? What if they had accidentally detected a transmission from an extraterrestrial civilization? The regularity of the pulses certainly suggested something engineered rather than natural. Hewish and his colleagues began referring to the signal internally as LGM-1 for Little Green Men. They weren't seriously proposing that aliens were responsible, but the name reflected the genuine uncertainty about what could possibly produce such a signal. They kept the discovery secret while they investigated further, not wanting to announce the detection of intelligent aliens only to discover a mundane explanation later. For weeks, the team worked in secret, checking and rechecking their equipment. They looked for any terrestrial source that could be mimicking an astronomical signal. They examined whether the signal could be coming from a satellite or aircraft. Nothing fit. The signal persisted, regular as clockwork, night after night, moving with the stars rather than with any human-made object. Then Bell found a second source, pulsing at a different rate from a different part of the sky, and then a third, and a fourth. The discovery of multiple pulsing sources was actually a relief. If the signals were artificial communications from alien civilizations, finding 4 of them scattered across the sky seemed improbable. It would require multiple civilizations independently deciding to send regular pulses toward Earth. But if the sources were a new type of natural object, finding several of them made perfect sense. Whatever process created one could create many. The universe doesn't usually produce single examples of any phenomenon. The team now felt confident enough to publish. In February 1968, they announced the discovery of pulsating radio sources, quickly shortened to Pulsars. The paper caused a sensation. Nothing like this had ever been detected before. But what were these objects? The 1.337-second period of the first pulsar provided a crucial constraint. For a signal to vary that quickly, the source must be small. If an object larger than about 3,000 miles tried to pulse coherently, different parts of it would get out of sync, because information cannot travel faster than light. This meant pulsars had to be compact objects, not ordinary stars. Thomas Gold at Cornell University proposed the answer almost immediately. Pulsars were rapidly rotating neutron stars. A neutron star is the collapsed core of a massive star that has exploded as a supernova. When a star several times more massive than the Sun exhausts its nuclear fuel, its core implodes catastrophically. The electrons and protons are crushed together to form neutrons, creating an object about 12 miles across but containing more mass than the Sun. The density is almost beyond comprehension. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. The gravitational field at the surface is about 200 billion times stronger than Earth's gravity. These extreme conditions give neutron stars extreme properties. When the original star collapses, conservation of angular momentum causes the neutron star to spin rapidly, just as an ice skater spins faster when pulling in their arms. A star that rotated once every few weeks can become a neutron star rotating many times per second. The neutron star also inherits the magnetic field of its parent star, but compressed into a much smaller volume. This amplifies the field enormously. Some neutron stars have magnetic fields trillions of times stronger than Earth's. Gould proposed that these intense magnetic fields channel radiation into beams that shoot out from the magnetic poles. As the neutron star rotates, these beams sweep across space like lighthouse beams. When a beam happens to point toward Earth, we detect a pulse. When it points away, the pulsar seems to turn off. The pulsing isn't the neutron star turning on and off, but rather the beam sweeping past our line of sight with each rotation. This elegant model explained all the observed properties of pulsars. The precise timing came from the stable rotation of a massive object. The variations in pulse shape came from the complex structure of the magnetic field. The gradual slowing of pulse rates over time came from the neutron star losing rotational energy as it radiates. The discovery was confirmed in spectacular fashion later that year when astronomers found a pulsar at the center of the Crab Nebula. The Crab Nebula is the remnant of a supernova explosion that Chinese astronomers recorded in 1054 AD. Finding a pulsar exactly where theory predicted there should be a neutron star provided overwhelming evidence that the model was correct. Pulsars weren't little green men. They were something arguably even more exotic, the ultra-dense corpses of dead stars, spinning faster than helicopter blades and emitting beams of radiation that sweep across the cosmos like celestial lighthouses. Jocelyn Bell had made one of the most important astronomical discoveries of the 20th century. But when the Nobel Prize was awarded in 1974, it went to Hewish and another colleague, Martin Ryle. Bell was excluded, a decision that remains controversial to this day. Many astronomers believe she deserved to share the prize for her meticulous observation and recognition of the anomaly. The Nobel Committee's decision has been criticized as reflecting the biases of the era regarding the contributions of graduate students and women in science. Bell herself has been remarkably gracious about the snub, but the scientific community has increasingly recognized her central role in the discovery. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics, worth $3 million. She donated the entire prize to fund scholarships for women, underrepresented minorities, and refugee students studying physics. The pulsar story established a template that would repeat throughout the history of radio astronomy. A strange signal is detected that seems to defy explanation. For a brief moment, the possibility of artificial origin is entertained. Then a natural explanation is found, but that explanation involves something more exotic than anyone had previously known to exist. The universe turns out to be stranger than we imagined, just not in the way we initially guessed. Pulsars became incredibly valuable tools for physics and astronomy. Their precise timing allows astronomers to detect tiny variations caused by passing gravitational waves. Binary pulsars, where a pulsar orbits another neutron star, have been used to confirm Einstein's predictions about general relativity and gravitational radiation. One pulsar system has even been found to host planets, worlds orbiting a dead star in a system nothing like our own. The strange signals from pulsars continue to yield discoveries more than 5 decades after Bell first noticed that bit of scruff on her chart paper. While pulsars were being understood, astronomers continued detecting other strange signals from across the cosmos. Some of these would eventually be explained by the same kinds of exotic objects. Others would point toward phenomena even more energetic and mysterious. In the 1970s, satellites designed to monitor nuclear weapons testing began detecting bursts of gamma rays from space. These gamma-ray bursts appeared randomly across the sky and lasted from fractions of a second to several minutes. Their origin was completely unknown. For decades, astronomers debated whether they came from relatively nearby sources within our galaxy or from extreme distances requiring almost unimaginable energy releases. The debate wasn't settled until 1997, when the Italian-Dutch satellite Beppo Sachs detected a gamma-ray burst and quickly determined its position with enough precision for optical telescopes to find the afterglow. The afterglow was associated with a distant galaxy, proving that gamma-ray bursts were extragalactic and therefore incredibly energetic. We now know that most gamma-ray bursts come from two types of events. Long bursts lasting more than 2 seconds are typically caused by the collapse of massive stars, when the core implodes not just to a neutron star, but all the way to a black hole, launching jets of material at nearly the speed of light. Short bursts lasting less than 2 seconds come from neutron star mergers, when two neutron stars in a binary system spiral together and collide. Both types of events represent the most violent explosions in the universe since the Big Bang itself. The pattern continued with other discoveries. Strange X-ray sources that flickered rapidly turned out to be matter falling onto neutron stars and black holes. Unusual radio sources at the centers of galaxies were revealed to be supermassive black holes, millions to billions of times more massive than the Sun. Each time, the signals seemed impossible until a new type of cosmic object was proposed to explain them. The universe kept introducing us to phenomena more extreme than science fiction had imagined. By the end of the 20th century, astronomers had catalogued thousands of pulsars, hundreds of gamma-ray bursts, and countless other high-energy sources. The sky that had seemed so serene and unchanging in visible light was revealed to be a violent, dynamic place in other wavelengths. Stars exploded, black holes fed, neutron stars collided, and all of it produced signals that traveled across the cosmos to reach our instruments. But among all these discoveries, one signal remained stubbornly unexplained. It had arrived on a summer night in 1977, lasting only 72 seconds before vanishing forever. The astronomer who found it had no context for understanding what he was seeing. It matched no known natural phenomenon. It appeared at exactly the frequency where scientists had predicted an intelligent civilization might broadcast, and despite more than 4 decades of investigation, no one has ever determined what caused it. The signal came from the direction of the constellation Sagittarius, not far from where Carl Jansky had first detected radio waves from space. It was detected by a radio telescope that had been specifically designed to search for extraterrestrial intelligence. And when the astronomer who discovered it saw the data, his reaction captured the profound strangeness of what he was looking at. He grabbed a red pen, circled the anomalous reading, and wrote a single word in the margin. That word became the signal's name, and the search for its explanation became one of the longest-running mysteries in the history of astronomy. The WOW signal, as it came to be called, represents something different from all the other strange signals we've discussed. It wasn't eventually explained by an exotic but natural phenomenon. It wasn't traced to a new type of stellar object. It simply arrived once, displayed characteristics that seemed almost designed to get our attention, and never repeated. To understand why this signal has fascinated and frustrated scientists for nearly half a century, we need to examine exactly what was detected that August night and why every attempt to explain it has fallen short. The Big Ear radio telescope didn't look like humanity's ear to the cosmos. It looked like a large, flat parking lot surrounded by metal scaffolding. Located at Ohio State University's Perkins Observatory, about 25 miles north of Columbus, the telescope consisted of a flat aluminum reflector the size of 3 football fields. Radio waves from space would hit this reflector and bounce toward a secondary reflector, which focused them into receivers that could analyze the incoming signals. The telescope couldn't be pointed at specific targets like a conventional dish antenna. Instead, it relied on Earth's rotation to sweep different portions of the sky past its field of view. Any given point in the sky would remain visible to Big Ear for exactly 72 seconds before Earth's rotation carried it out of view. This meant that any signal from space would last precisely 72 seconds, growing stronger as the source moved into the beam, peaking when it was centered, then fading as it moved out. The telescope had been operating since 1963, but in 1973, it was dedicated to a new purpose. Big Ear became part of the SETI program, the search for extraterrestrial intelligence, scanning the skies for signals that might indicate the presence of intelligent life elsewhere in the galaxy. The search focused on a specific frequency, 1420 MHz, corresponding to a wavelength of 21 centimeters. This frequency has special significance in radio astronomy. It's the emission line of neutral hydrogen, the most abundant element in the universe. Hydrogen atoms occasionally undergo a quantum transition that releases energy at precisely this frequency. Because hydrogen is everywhere, this frequency is well known to any civilization that has developed radio astronomy. SETI scientists reasoned that an intelligent species wanting to announce its presence would choose a frequency that other intelligent species would naturally be monitoring. The 1420 MHz hydrogen line was the obvious choice, a cosmic meeting point on the radio dial. There's another reason this frequency is attractive for interstellar communication. Radio noise from both natural sources and human technology tends to be lower in a range of frequencies between about 1000 and 10000 MHz. The hydrogen line sits comfortably within this quiet window. Furthermore, at nearby frequencies around 1720 MHz, hydroxyl molecules emit their own characteristic radiation. Hydrogen combined with hydroxyl makes water, the substance essential for life as we know it. The frequency range between the hydrogen line and the hydroxyl lines has been poetically named the water hole, like a gathering place where different species might come to meet. If aliens wanted to say hello, this is where we'd expect them to do it. Big Ear monitored the water hole continuously, recording signal strength as a series of alphanumeric characters on paper printouts. The system sampled the incoming signal every 12 seconds and assigned a character representing the intensity. Blank spaces indicated background noise levels. Numbers 1 through 9 represented increasing intensities above background. For signals even stronger than 9, the system used letters, with A representing 10 times background, B representing 11 times, and so on up through Z. The printouts looked like pages of seemingly random letters and numbers, and for years, that's exactly what they were. The volunteers who analyzed the data saw nothing but noise. Then came the night of August 15th, 1977. The telescope was performing its normal sweep of the sky. The receivers were recording. The printout was scrolling. At 11:16 p.m. Eastern Time, something extraordinary happened. A signal arrived from the direction of the constellation Sagittarius, just northwest of the globular cluster M55. The signal lasted exactly 72 seconds, matching the telescope's window on any point source perfectly. It rose in intensity as the source moved into the beam, peaked when centered, and faded as it moved out. The intensity sequence recorded on the printout read 6EQJ5. That sequence of characters doesn't look impressive at first glance, but consider what it means. The letter U represents a signal 30 times stronger than the background noise level. The letters E and Q represent intensities of 14 and 26 times background respectively. The entire sequence traced out the exact profile expected from a point source passing through the telescope beam. This wasn't random noise. This was a signal, and an intense one. The frequency was 1420.456 MHz, within 50 kHz of the hydrogen line. The bandwidth was extremely narrow, less than 10 kHz, far narrower than any known natural source produces. Natural radio sources emit across broad ranges of frequencies. Narrowband signals require either very special natural conditions or deliberate engineering. The signal matched almost perfectly what SETI scientists had predicted an alien transmission would look like. Jerry Amon discovered the anomaly 3 days later, on August 18th, while reviewing the printouts at home. Amon was a volunteer astronomer who had been helping analyze Big Ear data for years. He had seen countless printouts filled with meaningless noise. He had learned to recognize interference from terrestrial sources and the characteristic signatures of natural phenomena. What he saw in the 6E2J5 sequence was unlike anything he had encountered. The signal was too strong, too narrow, and too perfectly matched to the expected profile of an extraterrestrial transmission. Eamon grabbed a red pen and circled the sequence. In the margin, he wrote a single word that would become the signal's permanent name. Wow! It was a spontaneous expression of astonishment. Not a scientific designation, but the name stuck, and the WOW signal entered history as the most intriguing candidate for an extraterrestrial communication ever detected. The investigation began immediately. The first task was ruling out terrestrial interference. The signal had all the characteristics of something from space. It had risen and fallen over exactly 72 seconds, matching Earth's rotation. It had appeared at sidereal time, tracking with the stars rather than with the sun. Terrestrial signals don't behave this way. A car driving past the observatory wouldn't produce a signal that peaked at exactly the right moment. A malfunctioning electronic device wouldn't create such a narrow bandwidth. Aircraft and satellites were considered and rejected. The geometry didn't match. The signal had come from a fixed point in the sky that moved with the celestial sphere. The frequency was problematic for the interference hypothesis too. The 1420 MHz hydrogen line is protected by international agreement. No terrestrial transmitter is supposed to use it. This doesn't mean violations never occur, but the protected status reduces the likelihood of interference at that specific frequency. Astronomers began observing the same region of sky repeatedly, hoping to detect the signal again. Big Ear returned to the position dozens of times over the following weeks and months. Other telescopes joined the search. The Very Large Array in New Mexico, Arecibo in Puerto Rico, the Green Bank Telescope in West Virginia, all pointed at the coordinates where the WOW signal had originated. They found nothing. The signal never repeated. This non-repetition became the central frustration of the investigation. A single detection, no matter how intriguing, cannot be verified. Science requires reproducibility. Without a second detection, the WOW signal remained an anomaly rather than a confirmed phenomenon. Months turned into years. Years turned into decades. The search continued sporadically. Whenever telescope time became available, astronomers would occasionally return to the WOW signal coordinates, listen for a while, hear nothing, and move on to other projects. The Allen Telescope Array, designed specifically for SETI, monitored the region as part of its surveys. Various other SETI projects included the coordinates in their target lists. The result was always the same. Whatever had produced the WOW signal in 1977 had apparently fallen silent. The question of what caused the signal has generated numerous hypotheses over the decades. Some explanations invoke natural phenomena. Interstellar scintillation can briefly amplify weak radio sources, similar to how Earth's atmosphere makes stars twinkle in visible light. Perhaps an otherwise unremarkable natural source was briefly amplified by plasma in interstellar space, but this hypothesis struggles to explain the extremely narrow bandwidth of the signal. Natural amplification processes don't typically select such narrow frequency ranges. Another natural hypothesis involves hydrogen clouds in space. Neutral hydrogen pervades the galaxy, and under certain conditions, hydrogen masers can form. A maser is like a laser, but for microwaves, producing intense, narrow bandwidth radiation through stimulated emission. Perhaps a natural hydrogen maser produced the signal, but known hydrogen masers don't match the characteristics of the WOW signal very well. They're typically associated with star-forming regions or evolved stars, and no such objects exist at the signal's coordinates. In 2016 and 2017, astronomer Antonio Paris proposed a specific natural explanation that gained significant media attention. He suggested that two comets, designated 266P/Christensen and P2008Y2, might have been in the right part of the sky in August 1977. Comets are surrounded by vast clouds of hydrogen released as their ices sublimate. Paris argued that this cometary hydrogen could have produced the signal at the hydrogen line frequency. When comet 266P/Christensen returned to a favorable position in 2017, Paris observed it and claimed to have detected a signal consistent with his hypothesis. The comet explanation made headlines, with some media outlets declaring the mystery solved. but the scientific community was largely skeptical. Other researchers pointed out serious problems with the hypothesis. The WOW signal was extremely narrowband, while cometary hydrogen emission is typically broadband. The signal strength was far higher than expected from a cometary source at that distance. The position of the comets in 1977 didn't precisely match the WOW signal coordinates, and observations by other astronomers failed to replicate Paris's claimed detection from Comet 266P/Christensen. The comet hypothesis remains controversial at best, with many astronomers considering it unlikely. More exotic explanations venture into territory that scientists are understandably cautious about. Could the WOW signal have been a transmission from an extraterrestrial civilization? The signal matched the predictions for such a transmission remarkably well. It was at the right frequency, the hydrogen line where SETI searches focus. It was narrowband, as an engineered signal would be. It was strong, as if someone wanted to be noticed. It rose and fell over exactly 72 seconds, as a point source would. It came from a region of sky with no obvious natural source. If you asked a SETI scientist to describe what an alien signal might look like, they would describe something very much like the WOW signal. But extraordinary claims require extraordinary evidence, and a single unrepeated detection doesn't meet that standard. The alien hypothesis cannot be confirmed without repetition of the signal or detection of additional signals with similar characteristics. At the same time, the alien hypothesis cannot be definitively ruled out. The WOW signal remains consistent with an artificial origin. We simply don't have enough information to draw conclusions. There are reasons an alien signal might not repeat. Perhaps the transmission was a beacon that sweeps across the sky, and it simply hasn't pointed toward Earth again in the decades since. Perhaps it was a one-time transmission, a message sent once and never repeated. Perhaps the civilization that sent it no longer exists. Perhaps our subsequent observations were poorly timed, missing the signal during its active periods. Or perhaps the WOW signal wasn't artificial at all, and some natural explanation we haven't yet conceived is responsible. Jerry Amon, who discovered the signal and devoted considerable effort to understanding it over the following decades, remained cautiously agnostic. He never claimed the signal was extraterrestrial, but he also never endorsed any of the proposed natural explanations. In interviews, he emphasized how closely the signal matched what SETI researchers expected from an alien transmission, while acknowledging that a single detection couldn't prove anything. Amon continued investigating the WOW signal until his death in February 2022, at the age of 89. He never received a definitive answer to the mystery he had stumbled upon that August night in 1977. The WOW signal endures as a reminder that the universe can present us with puzzles that resist easy solution. It's tempting to imagine that all mysteries are eventually solved, that given enough time and effort, we can understand everything. The WOW signal challenges that comfortable assumption. Sometimes, the crucial information is simply unavailable. The signal arrived once, left an ambiguous record, and vanished. We may never know what caused it. The Big Ear radio telescope itself no longer exists. It was demolished in 1998 to make way for a golf course expansion despite protests from astronomers and SETI enthusiasts. The flat aluminum reflector that had captured the WOW signal was dismantled, and the site where humanity had its closest brush with possible extraterrestrial contact became a fairway. There's something melancholy about that transformation, the equipment that had listened to the cosmos replaced by a recreational facility. But the data from that August night survives. The printout with Eamon's red circle and handwritten WOW preserved in archives. The signal remains unexplained. The 72 seconds of mystery continue to intrigue new generations of scientists and enthusiasts. And the question of what produced that brief burst of narrowband radiation in 1977 remains open. Perhaps future technology will allow us to solve the puzzle. Perhaps we'll detect similar signals from elsewhere in the sky. Or perhaps the WOW signal will remain forever singular, a tantalizing hint of something we weren't quite able to grasp. For decades after the WOW signal, the search for unexplained cosmic signals continued without dramatic results. SETI projects accumulated thousands of hours of observations. Radio astronomers catalogued new pulsars and mapped the structure of the galaxy in ever greater detail. The WOW signal remained anomalous but lonely, a single unexplained event in an otherwise comprehensible cosmos. Then, in 2007, a graduate student examining archival data discovered something that would open an entirely new field of astronomy. The discovery didn't attract immediate attention. It took years for the scientific community to accept that something genuinely unprecedented had been found. But what Duncan Lorimer and his student David Narkevich pulled from old observations would prove to be one of the most mysterious classes of signals ever detected from space. The data came from the Parkes Radio Telescope in Australia, a 64-meter dish that has been operating since 1961. Parkes has made numerous important discoveries over the decades, including the detection of the first known quasar and the reception of television signals from the Apollo 11 moon landing. In 2001, astronomers had used Parkes to search for pulsars in the Small Magellanic Cloud, a dwarf galaxy orbiting the Milky Way. The observations had been processed and archived, the pulsars catalogued, the project completed. The data sat in storage for years, waiting for someone to take another look. Lorimer, a radio astronomer at West Virginia University, was looking for pulsars that previous analyses might have missed. He assigned his student Narkevich the task of reprocessing the archival Parkes data with improved techniques. In 2007, Narkevich found something strange. One observation contained a burst of radio waves lasting only 5 milliseconds, far too brief to be a pulsar, which emits regular pulses as it rotates. The burst was also extraordinarily bright, the most intense radio signal in that section of data by far, and it had a peculiar signature that suggested it had traveled a very long distance through space. When radio waves pass through plasma, the electrons in the plasma interact with the waves in a frequency-dependent way. Lower frequency waves are delayed more than higher frequency waves. This effect is called dispersion, and the amount of dispersion depends on how much plasma the signal has passed through. Within our galaxy, the interstellar medium contains enough free electrons to cause measurable dispersion for radio signals traveling across thousands of light-years. The burst that Narkevich found had an enormous dispersion measure, far larger than anything within the Milky Way could produce. The signal appeared to have traveled through intergalactic space, passing through not just our galaxy's interstellar medium, but also the thin plasma that fills the voids between galaxies. If the dispersion measure was interpreted correctly, this burst had originated billions of light-years away. The energy implications were staggering. For a burst to be detectable at such distances, it would need to release as much energy in 5 milliseconds as the Sun produces in a month. Nothing known in astronomy could explain such an event. Lorimer and his colleagues published their discovery in 2007, proposing that they had detected a new class of astronomical phenomenon. They called it a fast radio burst. The scientific community was skeptical. A single detection of something so extraordinary naturally raised suspicions. Perhaps the burst was instrumental error. Perhaps it was terrestrial interference that had somehow been recorded. Perhaps the dispersion measure had been misinterpreted. With only one example to study, it was impossible to rule out these possibilities. The Lorimer burst, as it became known, remained in scientific limbo for years. Some researchers believed it was genuine. Others considered it a curiosity, at best, an artifact at worst. Without additional detections, the question couldn't be resolved. Then in 2010 and 2011, the situation became more complicated rather than clearer. Sarah Burke-Spolar and her colleagues at Parkes detected additional burst-like signals with high dispersion measures. For a moment, it seemed like confirmation had arrived. But these new signals, dubbed peritons, had troubling characteristics. They appeared to come from multiple directions simultaneously, which is impossible for an astronomical source. They also occurred preferentially during business hours, suggesting a human origin. The periton mystery was solved in 2015, and the answer was almost comically mundane. The signals were being produced by microwave ovens in the observatory kitchen. When staff opened the microwave door before the heating cycle completed, the magnetron would produce a brief burst of radio emission that the telescope could detect. The peritons were literally caused by impatient astronomers and technicians heating their lunches. This discovery was embarrassing, but also clarifying. The peritons had characteristics that distinguished them from the original Lorimer burst. They appeared in multiple telescope beams simultaneously, while the Lorimer burst appeared in only one. They lacked certain polarization signatures that the Lorimer burst displayed. The microwave oven explanation actually strengthened the case that the original detection was genuine. The Lorimer burst didn't match the periton pattern. Whatever it wasn't interference from kitchen appliances. Meanwhile, additional fast radio burst candidates began accumulating. In 2012, a burst was detected by the Arecibo radio telescope in Puerto Rico, the first detection outside of Parkes. This was important because it showed the phenomenon wasn't specific to one instrument. If bursts were appearing at multiple observatories, they were more likely to be real astronomical events. By 2013, a team led by Dan Thornton had found 4 more bursts in Parkes archival data. The pattern was becoming clear. Fast radio bursts were rare but real. They came from all directions, suggesting an extragalactic distribution. They had enormous dispersion measures, consistent with cosmological distances. And they released fantastic amounts of energy in tiny fractions of a second. The question of what could possibly produce them remained wide open. Theoretical papers proliferated. Perhaps fast radio bursts came from colliding neutron stars, the merger releasing a final electromagnetic scream. Perhaps they came from evaporating black holes, the endpoint of Hawking radiation producing a radio flash. Perhaps they came from magnetars, neutron stars with extraordinarily powerful magnetic fields undergoing some kind of catastrophic rearrangement. Perhaps they came from cosmic strings, hypothetical defects in space-time from the early universe. Perhaps, some even suggested, they came from alien civilizations using unimaginably powerful transmitters. The breakthrough in understanding came in 2016, when astronomers discovered the first fast radio burst that repeated. The burst, designated FRB 121102, originally detected in 2012, was observed to produce additional bursts from the same location on the sky. This was revolutionary. If fast radio bursts were caused by cataclysmic events like neutron star mergers or black hole evaporations, each source could only burst once. The object producing the burst would be destroyed in the process. But a repeating source meant the underlying object survived each burst. Whatever was producing FRB 121102, it was doing so repeatedly without destroying itself. The repeating nature also allowed astronomers to study the source in ways impossible for one-time bursts. They could point multiple telescopes at the known location and wait for the next burst. They could observe simultaneously at different wavelengths. They could accumulate enough detections to pinpoint the position precisely. In 2017, a massive observing campaign succeeded in localizing FRB 121102 to a small dwarf galaxy about 3 billion light-years from Earth. The source was associated with a persistent radio source in that galaxy, a continuously emitting object that might be related to whatever was producing the bursts. The environment appeared extreme, with strong magnetic fields and dense plasma surrounding the source. The magnetar hypothesis gained strength. Magnetars are a special class of neutron stars with magnetic fields up to 1,000 times stronger than ordinary neutron stars. These fields are so intense that the crust of the star can crack under magnetic stress, producing starquakes. The rearrangement of the magnetic field during these events could theoretically release enormous amounts of energy. Perhaps FRB 121102 was a magnetar undergoing repeated magnetic outbursts. The decisive evidence came in April 2020. A magnetar in our own galaxy, designated SGR 1935 plus 2154, had been active for weeks, producing X-ray bursts typical of magnetar behavior. On April 28, the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, detected a millisecond duration radio burst from the magnetar. Simultaneously, the STARE-2 experiment in the southwestern United States detected the same burst. X-ray telescopes observed an X-ray burst at the same moment. For the first time, a fast radio burst had been detected from a known object, caught in the act across multiple wavelengths. The burst from SGR 1935 plus 2154 was weaker than extragalactic fast radio bursts, but the magnetar was also much closer. When astronomers calculated what the burst would look like from a typical FRB distance of billions of light-years, the energy matched. The mystery was not completely solved. The galactic magnetar burst was less energetic than the most powerful extragalactic bursts, raising questions about whether all fast radio bursts come from magnetars or whether multiple mechanisms might be involved. The repeating behavior of sources like FRB 121102 doesn't match the sporadic activity of galactic magnetars very well. Some fast radio bursts have properties that don't fit the magnetar model comfortably. The field is still young, with new discoveries arriving constantly. The CHIME telescope detects multiple fast radio bursts every day, accumulating a catalog of hundreds of sources. Some repeat frequently, others have been seen only once. Some show interesting temporal patterns. FRB 201-809-16b, for example, repeats on a 16-day cycle, with bursts clustering in a 4-day window and then nothing for 12 days. This periodicity might indicate orbital motion or rotation of something in the source environment. Other bursts show no periodicity, despite extensive monitoring. The application of fast radio bursts has expanded beyond understanding their origin. Because the dispersion measure depends on the amount of plasma along the line of sight, fast radio bursts can probe the intergalactic medium. Each burst serves as a flashlight, illuminating the diffuse gas between galaxies. Before fast radio bursts, this intergalactic medium was difficult to study. It's too thin to emit much radiation of its own. But fast radio bursts pass through it and accumulate dispersion that can be measured precisely. Astronomers have used fast radio bursts to confirm that about half of the ordinary matter in the universe exists in this diffuse intergalactic state, resolving a long-standing mystery about where all the normal matter was hiding. Fast radio bursts have gone from unexplained anomalies to valuable tools for cosmology in less than 2 decades. The original Lorimer burst that sat in an archive for 6 years before anyone noticed it helped launch a new field of astrophysics. Thousands of researchers now study fast radio bursts. Dozens of papers are published each month, and specialized instruments have been built specifically to detect them. The contrast with the WOW signal is instructive. Both were unexpected radio signals that seemed to violate known physics. Both initially raised questions about possible artificial origin, but fast radio bursts repeated, allowing scientists to study them in detail and eventually connect them to magnetars. The WOW signal appeared once and never again, leaving us with insufficient data to reach any conclusion. The lesson seems to be that the universe produces strange signals regularly, and patience combined with advancing technology usually provides explanations, but not always. Some signals may remain forever enigmatic, their origins lost to the one-time nature of their detection. Fast radio bursts also remind us how much remains to be discovered. 20 years ago, these events were unknown. Now they're observed daily. What other phenomena are occurring in the cosmos that our current instruments aren't designed to detect? What signals are arriving at Earth right now that we're not equipped to notice? The universe has consistently proven stranger than our theories predict, and there's no reason to think we've reached the end of the surprises. The discovery of pulsars in 1967 seemed to close a chapter on cosmic mystery. What had initially appeared to be possible alien signals turned out to be rapidly rotating neutron stars, exotic but natural objects that fit neatly into our understanding of stellar evolution. The little green men hypothesis was retired, and pulsars became tools for physics rather than targets for speculation. But the story didn't end there. Over the following decades, as astronomers discovered thousands of pulsars and studied them with increasing precision, they found that these cosmic clocks harbored mysteries of their own. Some pulsars behaved in ways that no theory could fully explain. Others displayed patterns so strange that scientists are still struggling to understand them. The lighthouse beams that seemed so elegantly simple turned out to be far more complex than anyone had anticipated. Pulsars are fundamentally simple objects in concept. Pulsars are fundamentally simple objects in concept. A neutron star rotates. Its magnetic field channels radiation into beams. The beams sweep across space. When a beam crosses our line of sight, we detect a pulse. The rotation is incredibly stable because neutron stars are massive and compact, resisting any force that would change their spin. This stability makes pulsars among the most precise clocks in the universe. The best-timed pulsars keep time more accurately than atomic clocks, varying by less than a microsecond over years of observation. Astronomers can predict exactly when each pulse will arrive, and any deviation from that prediction indicates something interesting happening either to the pulsar itself or to the space between the pulsar and Earth. This predictability is what makes pulsars valuable for tests of general relativity and searches for gravitational waves, but it's also what makes their occasional misbehavior so puzzling. The first hint that pulsars weren't as well behaved as expected came from the Vela pulsar in 1969, just 2 years after the original pulsar discovery. Vela is a relatively young pulsar, formed in a supernova explosion about 11,000 years ago. It rotates about 11 times per second, and its pulses had been arriving with clockwork regularity. Then, on a single day, the pulsar suddenly sped up. The rotation rate increased by a tiny but measurable amount, about 1 part in a million. This sudden acceleration was dubbed a glitch, borrowing computing terminology for an unexpected malfunction. The glitch was followed by a gradual recovery, with the pulsar slowly spinning back down toward its original rate over the following weeks. But the recovery wasn't complete. The pulsar settled into a new rotation rate slightly faster than before, as if some permanent change had occurred. Since that first detection, glitches have been observed in many pulsars. The Vela pulsar glitches approximately once every 3 years, making it one of the most frequently glitching pulsars known. The Crab pulsar, younger and more energetic, glitches about once per year on average. Some pulsars have been observed to glitch only once in decades of monitoring. Others have never glitched at all, despite extensive observation. The leading explanation for glitches involves the internal structure of neutron stars. The outer layer of a neutron star is a solid crust, a crystalline lattice of nuclei held together by an ocean of electrons. Below this crust lies a region filled with neutron-rich matter in a superfluid state, a quantum fluid that flows without friction. The superfluid interior rotates, but because it experiences no friction, it doesn't slow down at the same rate as the crust. The crust is coupled to the magnetic field, which radiates energy and causes the star to spin down gradually. The superfluid interior lags behind, storing angular momentum that the crust has lost. Eventually, the difference between the crust rotation and the interior rotation becomes too large. The coupling between the two layers suddenly transfers angular momentum from the interior to the crust, causing the abrupt spin-up we observe as a glitch. This model explains the basic phenomenon, but the details remain murky. Why do some pulsars glitch frequently while others never glitch at all? What determines the size of a glitch? Why does the recovery process vary so much between different pulsars and even between different glitches in the same pulsar? The situation became even stranger with the discovery of anti-glitches. In 2012, astronomers observed a magnetar, a neutron star with an extremely powerful magnetic field, suddenly slow down rather than speed up. This was the opposite of a normal glitch, a sudden decrease in rotation rate rather than an increase. The anti-glitch couldn't be explained by the superfluid angular momentum transfer model, which only predicts spin-ups. Something different was happening inside this star, perhaps a rearrangement of the magnetic field or a change in the coupling between different internal layers. Only a handful of anti-glitches have been observed, making them difficult to study systematically. Each one challenges theorists to explain how a neutron star can suddenly lose angular momentum rather than gain it. Beyond glitches, some pulsars exhibit even stranger behavior. Intermittent pulsars switch between active and quiet states, sometimes remaining detectable for weeks and then becoming invisible for months. The first intermittent pulsar was discovered in 2006, designated PSR B1931+24. This pulsar behaves normally for about 5 to 10 days, emitting regular pulses that can be timed precisely. Then it turns off. For the next 25 to 35 days, no pulses are detected at all. Then it turns back on, and the cycle repeats. The switching appears to be related to changes in the pulsar's magnetosphere, the region of magnetic field and plasma surrounding the neutron star. When the pulsar is active, charged particles flow through the magnetosphere and generate radio emission. When it's quiet, this particle flow apparently stops. But what triggers the switching? What determines the timescales? The physics remains poorly understood. The quiet state isn't just a period of reduced emission. The pulsar actually spins down at a different rate when it's quiet compared to when it's active. During active phases, the spin-down rate is about 50% higher than during quiet phases. This indicates that the radio emission is somehow connected to the angular momentum loss, but the relationship is more complex than simple models suggest. The energy carried away by radio waves is tiny compared to the total spin-down energy, so the radio emission itself isn't causing the different spin-down rates. Instead, both the radio emission and the enhanced spin-down must be symptoms of some underlying magnetospheric state that switches on and off. Understanding intermittent pulsars might reveal fundamental physics about how neutron star magnetospheres work, but the small number of known examples limits what we can learn. Another class of puzzling pulsars exhibits nulling, where the pulse emission drops to undetectable levels for periods ranging from a single pulse to hundreds of pulses before resuming. Nulling pulsars don't disappear for weeks like intermittent pulsars, but they randomly miss beats in their otherwise regular rhythm. Some pulsars null for about 1% of the time, occasionally skipping a pulse but mostly behaving normally. Others null for more than half the time, producing pulsars sporadically rather than regularly. The nulling appears to be random, with no predictable pattern to when a pulsar will turn off or turn back on. What's happening during nulls is unclear. The pulsar is still rotating, still generating the magnetic field configuration that produces pulses, but the radio emission simply doesn't appear. Perhaps the emission is being produced but beamed in a different direction. Perhaps the particle flows that generate radio waves are temporarily disrupted. Perhaps something about the plasma in the magnetosphere changes in ways we don't understand. Null pulses are like missing heartbeats from the cosmic clock, brief silences that punctuate the regular rhythm without any obvious cause. Mode switching adds another layer of complexity. Some pulsars alternate between different pulse profiles, switching between modes that look distinctly different. A pulsar might emit pulses with 2 peaks in one mode and a single peak in another mode. The switching happens suddenly, with no gradual transition between modes. The different modes often have different polarization characteristics, indicating changes in the geometry of the emission region. Like nulling, mode switching appears random. A pulsar might stay in one mode for hours, then switch to another mode for minutes, then switch back. The timescales and patterns vary between different pulsars and even vary over time for the same pulsar. Theorists have proposed various explanations involving changes in the magnetospheric currents or shifts in the emission altitude above the neutron star surface. None of these explanations is fully satisfactory. Mode switching remains a phenomenon in search of a theory. Perhaps the strangest pulsars of all are the rotating radio transients, or RRATs. These objects were discovered in 2006, when astronomers found radio sources that emitted occasional individual pulses but no continuous pulsation. Looking at a RRAT, you might see one pulse, then nothing for several minutes, then another pulse, then nothing for half an hour. The pulses come from a fixed location on the sky and show the characteristic dispersion of radio waves that have traveled through interstellar space, so they're definitely astronomical rather than terrestrial. When astronomers accumulated enough pulses to search for periodicity, they found that RRATs are indeed rotating neutron stars. The pulses occur at regular intervals corresponding to the rotation period, but only a tiny fraction of the rotations produce a detectable pulse. A typical RRAT might emit one observable pulse for every 100 or 1,000 rotations. Why do RRATs only occasionally produce visible pulses? Several possibilities have been proposed. Perhaps RRATs are extreme nullars, pulsars, whose emission turns off for the vast majority of the time. Perhaps their beams are very narrow, barely grazing Earth's line of sight, so that only occasional pulses are strong enough to detect. Perhaps RRATs represent an older population of pulsars whose emission is dying out, producing only rare final gasps of radiation. Perhaps they're a distinct class of neutron stars with different magnetic field configurations or internal structures. The discovery of RRATs raised an uncomfortable question for astronomers. If these sporadically emitting objects exist in significant numbers, how many have we missed entirely? A RAT that emits one detectable pulse per day might never be noticed by a survey that observes each patch of sky for only a few minutes. Population estimates suggest that RRATs might outnumber normal pulsars, implying that our census of neutron stars is seriously incomplete. The cosmos may be filled with dead stars that only occasionally whisper in our direction, their signals too intermittent for us to notice. The millisecond pulsars present their own mysteries. These are the fastest spinning pulsars, rotating hundreds of times per second. They're thought to be old pulsars that have been spun up by accreting matter from a companion star. The incoming matter transfers angular momentum to the neutron star, gradually increasing its rotation rate over millions of years. The record holder PSR J1748-2446 AD rotates 716 times per second. The surface at the equator of this star is moving at about 24% of the speed of light. Any faster and the star would tear itself apart, the centrifugal force overcoming gravity at the equator. This pulsar exists near the theoretical maximum rotation rate for a neutron star, pushing the limits of what matter can endure. Millisecond pulsars are extraordinarily stable timekeepers because their rapid rotation gives them tremendous angular momentum, but even they show timing irregularities that remain unexplained. These irregularities are much smaller than glitches, subtle variations in pulse arrival times that accumulate over years of observation. They might result from tiny changes in the pulsar's shape, variations in the interstellar medium between the pulsar and Earth, or physics we haven't identified yet. Pulsar timing arrays use networks of millisecond pulsars as galaxy-sized gravitational wave detectors. The idea is elegant. Gravitational waves passing through the galaxy should cause correlated variations in pulse arrival times from pulsars in different directions. By monitoring many pulsars precisely over years, astronomers can search for these correlations and detect gravitational waves with wavelengths measured in light years. The technique has recently succeeded, with multiple pulsar timing arrays detecting evidence of a gravitational wave background, a persistent rumble of space-time vibrations probably produced by merging supermassive black holes throughout the universe. But the signals are at the edge of detectability, and unexplained noise in pulsar timing data makes the analysis challenging. Understanding where this noise comes from and how to remove it is crucial for gravitational wave astronomy. The zoo of pulsar behaviors reveals how much we still don't understand about these objects. We know they're rotating neutron stars. We know they have intense magnetic fields. We know they emit beamed radiation that we detect as pulses. But the details of how the emission is produced, why it varies, and what determines the differences between individual pulsars remain areas of active research. Every few years, a pulsar is discovered that doesn't fit existing categories, forcing theorists to expand their models. The lighthouse metaphor that seemed so complete in 1968 has proven to be only a first approximation to far more complex reality. Strange signals continue to arrive from these cosmic clocks, challenging us to understand the physics of matter under the most extreme conditions the universe can create. In the autumn of 2015, a star located about 1,400 light-years from Earth became the most famous star in the galaxy. It wasn't particularly large or luminous. It wasn't exploding or collapsing or doing anything obviously dramatic, but its light was flickering in ways that no astronomer could explain, dimming by amounts that seemed to violate everything we knew about how stars work. For a brief, exhilarating moment, serious scientists found themselves discussing the possibility that we had detected an alien megastructure, a vast engineering project constructed by an intelligent civilization around their sun. The star's official designation was KIC 8462852, a forgettable string of characters identifying it as one of hundreds of thousands of stars observed by the Kepler Space Telescope, but it quickly acquired other names. Tabby's star, after the astronomer Tabitha Boyajian, who led the investigation. Boyajian's star. The WTF star, where WTF officially stood for Where's the Flux? The names reflected the mixture of scientific curiosity and public excitement that surrounded this peculiar object. The Kepler Space Telescope was launched in 2009 with a specific mission to find planets orbiting other stars by watching for the tiny dips in brightness that occur when a planet passes in front of its host star. This transit method requires extraordinary precision. Earth passing in front of the Sun, as seen from a distant star, would block only about 1/100% of the Sun's light. Jupiter would block about 1%. To detect such small changes, Kepler stared at the same patch of sky for years, monitoring the brightness of more than 150,000 stars with exquisite sensitivity. The spacecraft was phenomenally successful, discovering thousands of exoplanets and revolutionizing our understanding of planetary systems. But Kepler generated far more data than professional astronomers could analyze in detail. To help process this flood of information, researchers created Planet Hunters, a citizen science project that enlisted volunteers to examine Kepler light curves and flag interesting patterns. The human eye is remarkably good at spotting anomalies that automated algorithms might miss. Volunteers were shown graphs of stellar brightness over time and asked to mark anything unusual. In 2011, several Planet Hunters volunteers noticed that KIC 8462852 was doing something strange. The star's brightness was dipping, but not in the smooth, symmetric way expected from a transiting planet. The dips were irregular, varying in depth and duration. Some were shallow, dimming the star by a fraction of a percent. Others were deep, blocking up to 22% of the star's light. That number alone was extraordinary. The largest planet, even a giant larger than Jupiter, could only block about 1% of a star like this. What could possibly block 22%? The volunteers flagged the star for professional attention, and the data eventually reached Tabitha Boyajian, then a postdoctoral researcher at Yale University. Boyajian assembled a team to investigate the anomalies, and what they found only deepened the mystery. The dips weren't periodic. A planet orbiting a star would produce regular, predictable transits, but KIC 8462852 dimmed at seemingly random intervals. The dips weren't symmetric. A spherical planet would produce a smooth dimming curve as it crossed the star's disk, but these dips had irregular, jagged shapes. Some dips lasted hours, others lasted days. The patterns seemed almost chaotic. Boyajian's team published their findings in 2016, presenting the data without claiming to have an explanation. The paper was titled, "Where's the Flux?" Acknowledging the bafflement that the star had caused. The authors systematically considered and rejected various hypotheses. Instrumental error was ruled out because other stars on the same detector showed no anomalies. A transiting planet was ruled out by the depth and irregularity of the dips. A binary companion star was ruled out by the absence of radial velocity variations. A protoplanetary disk of gas and dust was ruled out because the star was too old. It showed none of the infrared excess that young, dusty stars exhibit. A swarm of comets passing in front of the star was proposed as a possibility, though even this explanation required unusual circumstances. What would cause hundreds of comets to pass between us and the star in such a short time? Then the story took an unexpected turn. Jason Wright, an astronomer at Penn State University, had been thinking about how we might detect extraterrestrial civilizations through their engineering projects rather than their radio signals. A sufficiently advanced civilization might construct enormous structures around their star to capture its energy, an idea proposed by physicist Freeman Dyson in 1960. A complete Dyson sphere enclosing a star entirely would be invisible at optical wavelengths but bright in infrared, radiating waste heat from the captured energy. But a partially complete Dyson sphere, still under construction, might produce exactly the kind of irregular dimming that KIC 8462852 was displaying. Structures orbiting the star at different distances would block different amounts of light at different times, creating the chaotic pattern that Kepler had recorded. Wright co-authored a paper discussing the alien megastructure hypothesis, carefully noting that it was a last resort after natural explanations had been considered and found wanting. He emphasized that extraordinary claims require extraordinary evidence, and that the alien hypothesis should motivate further investigation rather than premature conclusions. The media seized on the alien angle. Headlines around the world announced the possible discovery of an alien megastructure. The story spread virally, captivating millions of people who rarely paid attention to astronomical research. Tabby's star became a cultural phenomenon. Late-night talk show hosts joked about it. Social media exploded with speculation. The public imagination, always eager for evidence of extraterrestrial intelligence, embraced the possibility that we had finally found something. SETI researchers joined the investigation. The Allen Telescope Array pointed at KIC 8462852, listening for artificial radio signals that might accompany an alien construction project. Breakthrough Listen, the most well-funded SETI initiative in history, prioritized the star for intensive observation. They searched for narrowband signals like the WOW signal, broadband signals that might indicate industrial activity, and laser pulses that could serve as optical communications. The results were negative. No artificial signals were detected at any wavelength. The silence didn't prove that aliens weren't responsible for the dimming, but it removed one potential line of evidence that could have supported the hypothesis. Meanwhile, astronomers mobilized to observe the star at every opportunity. The key question was whether new dimming events could be caught in the act and studied in detail. Kepler had recorded historical dips, but understanding what was causing them required real-time observation across multiple wavelengths. If the dimming was caused by solid objects, like alien megastructures or asteroids, all wavelengths of light would be blocked equally. If the dimming was caused by dust, shorter wavelengths would be blocked more than longer wavelengths because small particles interact more strongly with blue light than red light. This wavelength-dependent dimming, called reddening, would be a signature of dust rather than solid structures. In May 2017, Tabby's star began dimming again, and this time astronomers were watching. Telescopes around the world captured the event, measuring the star's brightness at optical, infrared, and ultraviolet wavelengths. The results were definitive. The dimming was wavelength-dependent, with blue light blocked more than red light. Dust, not solid objects, was responsible for the dips. The alien megastructure hypothesis effectively died with that observation. Whatever was orbiting KIC 8462852, it wasn't an engineered structure. It was clouds of tiny particles, probably less than a micrometer in size, producing the characteristic reddening of a dusty environment. But where was the dust coming from? The star is too old to have a primordial debris disk. Young stars are often surrounded by disks of gas and dust left over from their formation, but these disks dissipate within tens of millions of years. KIC 8462852 is about 1 billion years old, far too mature to retain such a disk naturally. Something must be producing fresh dust, replenishing the particles that would otherwise disperse into space. The comet hypothesis, proposed in the original paper, remained viable. Perhaps a family of comets had recently been disrupted, perhaps by a close encounter with a passing star, and was now shedding material as the fragments passed close to KIC 8462852 and sublimated. The dust from sublimating comets could produce irregular dimming as different clumps of debris crossed our line of sight. Another possibility was a recent planetary collision. If two planets or large asteroids had collided in the system within the past few thousand years, the debris from the collision could still be spreading through the system. The collision hypothesis would explain the dust without requiring an unusual cometary event. Such collisions are rare but not unprecedented. Our own moon is thought to have formed from a giant impact early in Earth's history. The dimming pattern might be showing us the aftermath of a similar catastrophe in another star system. Further observations revealed additional complexity. Archival photographs showed that KIC 8462852 had dimmed by about 14% over the past century, a gradual long-term fading in addition to the dramatic short-term dips. This secular dimming was harder to explain than the dips. Dust clouds don't persist for centuries. The particles would be pushed away from the star by radiation pressure or would spiral inward due to drag effects. Some mechanism must be continuously producing new dust, or the long-term dimming must have a different cause than the short-term dips. The mystery of Tabby's star is not fully solved. We know the dips are caused by dust, not solid objects, but we don't know where the dust comes from or why this particular star is behaving so unusually. No other star in the Kepler sample shows the same pattern, making KIC 8462852 apparently unique among hundreds of thousands of observed stars. Whatever is happening there is either extremely rare or requires a specific combination of circumstances that we haven't identified. The star continues to be monitored, and each new dimming event provides additional data. Perhaps eventually we'll accumulate enough observations to determine whether comets, collisions, or something else entirely is responsible. The saga of Tabby's star illustrates how science actually works. An anomaly was detected. Multiple hypotheses were proposed, including exotic possibilities. Observations were gathered to distinguish between hypotheses. The data ruled out the most exciting explanation and supported a more mundane one. Dust is less glamorous than aliens, but it's the answer the evidence supports. The episode also demonstrated the tension between scientific caution and public excitement. When Jason Wright discussed the alien megastructure hypothesis, he did so carefully, presenting it as a possibility to be investigated rather than a conclusion to be embraced. But nuance doesn't travel well through media channels. Headlines stripped away the caveats, presenting alien megastructures as a leading explanation rather than a last resort. Millions of people heard about Tabby's star and came away with the impression that astronomers had found something genuinely alien. The disappointment when the dust explanation emerged was palpable. Comment sections and social media filled with accusations that scientists had hyped the alien hypothesis for attention and then walked it back when pressed. This wasn't really fair to the researchers, who had been appropriately cautious throughout, but it reflected genuine frustration among a public hungry for evidence of extraterrestrial intelligence. The search for such evidence continues. Tabby's star wasn't an alien megastructure, but that doesn't mean alien megastructures don't exist. It doesn't mean we shouldn't look for them. The observation that KIC 8462852's dimming is wavelength dependent provides a template for future searches. If we ever find a star that dims without reddening, that blocks all wavelengths equally, we'll have a candidate worth investigating more seriously. The tools developed to study Tabby's star, the networks of observers ready to respond to dimming events, the techniques for multi-wavelength follow-up, all remain available for future anomalies. The universe is vast enough that genuine alien engineering projects might exist somewhere. We simply haven't found one yet. In the meantime, Tabby's star reminds us that even disappointments can be scientifically valuable. We've learned that some stars can exhibit extreme photometric behavior without requiring exotic explanations. We've developed methods for rapid follow-up of transient events. We've engaged millions of people in thinking about the cosmos and their place within it. The alien megastructure hypothesis generated more public interest in astronomy than a dozen normal discoveries combined. Perhaps that enthusiasm, even if it was ultimately directed toward a dusty star rather than an alien civilization, will inspire the next generation of scientists to continue the search. The strange signals we've explored so far have come from tremendous distances. The WOW signal originated from somewhere in the direction of Sagittarius. Fast radio bursts arrive from galaxies billions of light-years away. Pulsars beam their radiation across thousands of light-years. Even Tabby's star sits 1,400 light-years from Earth. These vast distances make investigation difficult. We can observe, we can analyze, but we cannot visit. We cannot send probes to examine these sources up close or conduct experiments to test our hypotheses directly. But strange signals don't only come from the depths of interstellar space. Some of the most puzzling signals have originated much closer to home, within our own solar system. These nearby mysteries should be easier to solve. We can send spacecraft to investigate. We can observe with unprecedented detail. Yet some of these signals have proven just as difficult to explain as anything from the distant cosmos. The proximity that should make understanding easier sometimes only makes the mystery more frustrating. Saturn, the ringed giant of the outer solar system, has been broadcasting radio signals since before humans existed. Like Jupiter, Saturn has a powerful magnetic field that generates radio emissions through interactions with charged particles in its environment. When the Cassini spacecraft arrived at Saturn in 2004, beginning what would become a 13-year mission, scientists expected to use these radio emissions to determine something fundamental about the planet: how fast it rotates. This seems like it should be simple. You watch the planet spin, you time how long a rotation takes. But Saturn presents a unique challenge. The planet has no solid surface to track. Its visible features are bands of clouds that move at different speeds depending on latitude, driven by winds rather than the planet's underlying rotation. The most reliable way to determine the rotation rate of a gas giant is to measure its magnetic field, which is anchored deep in the planet's interior and rotates with the bulk of the planet. Jupiter's magnetic field is tilted about 10 degrees from its rotation axis, creating a wobble in radio emissions that clearly reveals the rotation period. Saturn's magnetic field is different. It's almost perfectly aligned with the rotation axis, within about 1 degree. This alignment means there's no wobble, no obvious periodic variation to measure. Scientists turn to another approach: Saturn's auroras. The brilliant light shows at its poles, created by charged particles funneling along magnetic field lines, produce distinctive radio emissions called Saturn kilometric radiation. These emissions were expected to vary with the planet's rotation, providing an indirect measure of the rotation period. The Voyager spacecraft had measured this periodicity in the early 1980s, finding a rotation period of about 10 hours and 39 minutes. But when Cassini arrived 2 decades later and began monitoring Saturn kilometric radiation, something was wrong. The period had changed. It now appeared to be about 10 hours and 45 minutes, roughly 6 minutes longer than Voyager had measured. This was deeply puzzling. A planet the size of Saturn cannot change its rotation rate by 6 minutes over just 2 decades. The angular momentum of Saturn is so enormous that altering its spin would require energy far beyond anything available in the Saturnian system. The planet itself wasn't spinning differently. Something else was affecting the radio emissions. The mystery deepened when scientists realized that the northern and southern hemispheres of Saturn were producing radio emissions with different periods. The northern aurora suggested one rotation rate, while the southern aurora suggested another. This was physically impossible if the emissions were directly tied to the planet's rotation. Saturn couldn't be rotating at 2 different speeds simultaneously. The solution, eventually worked out over years of Cassini observations, involved the solar wind and Saturn's unusual magnetic geometry. Because Saturn's magnetic field is so closely aligned with its rotation axis, the solar wind can influence the magnetosphere in ways that don't happen at Jupiter or Earth. Changes in solar wind pressure cause the auroral regions to shift, altering the apparent periodicity of the radio emissions. The radio emissions weren't tracking Saturn's rotation directly. They were tracking a complex interaction between the magnetosphere and the varying solar wind. The different periods in the northern and southern hemispheres resulted from different solar wind conditions at different times. Saturn's true rotation period remains somewhat uncertain even today. Best estimates place it around 10 hours and 33 minutes, but the exact value is still debated. A fundamental property of one of the largest planets in our solar system, a world we've orbited for over a decade, remains imprecisely known because its signals misled us. Jupiter, the largest planet, produces its own strange radio signals, and humans can detect them with surprisingly simple equipment. Jupiter is the brightest radio source in the sky after the Sun, and amateur astronomers with backyard antennas can pick up its emissions. The planet's rapid rotation, powerful magnetic field, and volcanic moon Io combine to create a complex radio environment. Io orbits deep within Jupiter's magnetic field, and its volcanoes spew sulfur dioxide into space, where it becomes ionized and forms a donut-shaped torus of plasma around Jupiter. Electrical currents flow along magnetic field lines, connecting Io to Jupiter's atmosphere, carrying millions of amperes and generating intense radio bursts. These Io-related emissions are the strongest, but Jupiter also produces non-Io emissions from other interactions in its magnetosphere. The radio signals vary dramatically, sometimes appearing as steady hiss and other times as sharp bursts. The complexity rivals anything produced by distant cosmic sources. The Juno spacecraft, which arrived at Jupiter in 2016, has revealed radio phenomena that scientists didn't anticipate. Juno flies closer to Jupiter than any previous mission, passing within a few thousand miles of the cloud tops on each orbit. From this vantage point, the spacecraft has detected radio emissions from lightning storms deep in Jupiter's atmosphere. These Jovian lightning strikes are far more powerful than anything on Earth, and they produce radio waves that Juno can observe as it passes overhead. The spacecraft has also mapped the three-dimensional structure of Jupiter's radio emissions, revealing that the emissions come from different altitudes and latitudes depending on their frequency. The picture that emerges is of a radio environment far more intricate than ground-based observations had suggested. Jupiter is essentially a natural radio station, broadcasting on many channels simultaneously, each channel revealing different aspects of the planet's magnetic field, atmosphere, and moons. Moving inward toward the Sun, we encounter mysteries closer to Earth. Our own moon, so familiar and so thoroughly explored, produces signals that weren't fully understood until recently. The moon has no global magnetic field today. Its iron core is small and no longer generates a dynamo like Earth's core does. But scattered across the lunar surface are patches of magnetized rock, miniature magnetic fields that create localized effects on the space environment. These lunar magnetic anomalies interact with the solar wind, the stream of charged particles flowing outward from the Sun. Where the magnetic fields are present, they can deflect the solar wind, creating mini magnetospheres that shield the surface beneath them. The shielding affects how the solar wind weathers the lunar soil, creating visible bright swirls on the surface where the protected soil hasn't been darkened by solar wind exposure. The Reiner Gamma Formation, visible through small telescopes as a bright splash on the Moon's western hemisphere, is the most famous of these magnetic swirls. Spacecraft orbiting the Moon have detected the signatures of these interactions. The solar wind piles up against the magnetic barriers, slows down, and diverts around them. Some particles are reflected back into space. The process creates measurable effects on the local plasma environment that lunar orbiters can observe. But the origin of the magnetic anomalies remains debated. One hypothesis suggests they're remnants of an ancient global magnetic field that the Moon possessed billions of years ago when its core was still molten and convecting. When the dynamo shut down, most of the magnetism was lost, but some was preserved in rocks that cooled and locked in the ambient field. Another hypothesis proposes that large asteroid impacts magnetized the crust through shock effects and interaction with plasma generated during the impact. The two hypotheses predict different distributions and characteristics for the magnetic anomalies, but the available data hasn't definitively distinguished between them. Even our nearest celestial neighbor harbors magnetic mysteries we haven't fully solved. The strangest signal from within our solar system in recent years came not from a planet or moon, but from an interstellar visitor. In October 2017, astronomers using the Pan-STARRS telescope in Hawaii discovered an object moving through the inner solar system on a trajectory unlike anything seen before. Its orbit was hyperbolic, meaning it wasn't bound to the sun. It had come from interstellar space and would return to interstellar space, just passing through our solar system on a journey between the stars. The object was named Oumuamua, a Hawaiian word meaning scout or messenger. It was the first confirmed interstellar object ever observed, a piece of another star system visiting our own. Oumuamua was strange from the beginning. Its brightness varied dramatically as it tumbled through space, suggesting an extremely elongated shape. Estimates based on the light curve suggested the object was perhaps 400 meters long, but only 40 meters wide, a 10-to-1 aspect ratio, unlike any asteroid or comet in our solar system. Its color was dark red, consistent with long exposure to cosmic radiation during its journey through interstellar space. But the object showed no coma, no fuzzy halo of gas that would indicate volatile ices sublimating in the sun's heat. This was puzzling because interstellar objects should contain pristine ices from their formation in a distant planetary system. A comet from another star should behave like a comet when it approached our sun. Then came the most puzzling observation of all. As Oumuamua moved away from the sun, tracking its trajectory revealed a small but significant anomaly. The object was accelerating slightly, not decelerating as gravity alone would predict. Something was pushing it away from the sun, adding a tiny extra velocity beyond what orbital mechanics could explain. Comets routinely show such non-gravitational acceleration because gas jets from sublimating ice act like small rockets, pushing the comet off its purely gravitational path. But Oumuamua showed no evidence of outgassing. No gas had been detected spectroscopically. No dust had been observed. If jets were responsible for the acceleration, they were somehow invisible. Several natural explanations have been proposed. Perhaps Oumuamua was outgassing hydrogen, which is extremely difficult to detect. Solid hydrogen could have accumulated on the object during its long journey through cold interstellar space and was now sublimating invisibly. Perhaps the object was extremely porous and low density, allowing solar radiation pressure to push it more effectively than a denser object. Perhaps tidal forces from the sun had caused it to fragment slightly, and the recoil from ejected fragments was providing the acceleration. None of these explanations is entirely satisfying, and the data are insufficient to distinguish between them. Avi Loeb, a prominent Harvard astronomer, proposed a more provocative hypothesis. He suggested that Oumuamua might be an artifact of alien technology, perhaps a solar sail or a piece of space debris from another civilization. The acceleration would be naturally explained if Oumuamua were a thin, lightweight object pushed by solar radiation pressure. The elongated shape could represent an intentional design rather than a natural formation. Loeb wrote a book arguing for the alien hypothesis, generating significant media attention and scientific controversy. Most astronomers consider the alien hypothesis premature at best. Oumuamua's properties are unusual, but not impossible for a natural object. We have only observed one interstellar visitor in detail. Perhaps such objects simply have different characteristics than we expected based on our solar system's inventory. The Vera Rubin Observatory, scheduled to begin operations soon, is expected to discover many more interstellar objects. If Oumuamua was typical, we'll see more like it. If it was genuinely anomalous, future discoveries might look different. Until then, the first messenger from the stars remains an enigma. Our own spacecraft have sometimes become sources of mysterious signals. The Pioneer anomaly puzzled scientists for decades before being resolved. Pioneer 10 and Pioneer 11, launched in 1972 and 1973 respectively, were the first spacecraft to visit Jupiter and Saturn, and the first to travel on trajectories that would carry them out of the solar system entirely. For years after their planetary encounters, NASA continued tracking the spacecraft, monitoring their positions through the Doppler shift of their radio signals. By the 1980s, analysts noticed something strange. Both Pioneer spacecraft were slightly closer to the Sun than they should have been. The discrepancy was tiny, corresponding to an extra acceleration toward the Sun of about 8/10 billionths of a meter per second squared. but it was consistent and growing. Something was decelerating the spacecraft beyond the known gravitational influences. The Pioneer anomaly generated tremendous interest among physicists. Some proposed that it indicated a modification to general relativity, that gravity might behave differently at large distances or low accelerations than Einstein's equations predicted. Others suggested dark matter drag or other exotic physics. The possibility that we had discovered something fundamentally new about the universe was exciting enough that the anomaly attracted serious theoretical attention for years. But the resolution, when it came, was more mundane. The Pioneer spacecraft carried radioisotope thermoelectric generators, power sources that produced electricity from the heat of decaying plutonium. This heat had to go somewhere, and it radiated away into space. But the radiation wasn't symmetric. The design of the spacecraft meant that slightly more heat was radiated toward the front than toward the back. This asymmetric thermal radiation produced a tiny but measurable thrust, pushing the spacecraft slightly toward the sun. When scientists conducted detailed thermal modeling of the spacecraft, accounting for how heat flowed through the structure and radiated into space, the calculated thrust matched the observed anomaly almost exactly. The Pioneer anomaly wasn't new physics, it was old physics. The basic principle that radiation carries momentum applied to a complex engineering system in a way that hadn't been fully appreciated. These solar system mysteries share a common lesson. Proximity doesn't guarantee understanding. We can send spacecraft, we can observe in detail, we can accumulate years of data, and still the signals can mislead us. Saturn's radio emissions suggested a rotation rate that was wrong. Oumuamua accelerated for reasons we still debate. The Pioneer spacecraft seemed to violate the laws of motion until patient analysis revealed a mundane explanation. The universe is tricky, even in our own backyard. The strange signals from nearby demand the same rigorous investigation as signals from across the cosmos, and sometimes they prove just as difficult to interpret. Everything we've explored so far has involved signals that arrived unexpectedly. Pulsars were discovered during a survey meant to study something else entirely. Fast radio bursts emerged from archival data that had sat unexamined for years. The WOW signal was captured by a telescope that happened to be pointed in the right direction at the right time. These accidental discoveries have taught us that the universe is full of phenomena we never anticipated. But alongside these serendipitous detections, a parallel effort has been underway for more than 60 years. Scientists have deliberately searched for signals that could only be artificial, transmissions from intelligent civilizations elsewhere in the galaxy. This is SETI, the search for extraterrestrial intelligence, and it represents one of the most profound scientific endeavors humans have ever undertaken. The question it seeks to answer is simple to state and staggering in its implications. Are we alone? The modern SETI era began in 1959 when physicist Giuseppe Cocconi and Philip Morrison published a paper in the journal Nature titled "Searching for Interstellar Communications." They argued that radio waves offered the most practical means for civilizations separated by light years to communicate. Radio signals travel at the speed of light, can be generated and detected with relatively modest technology, and pass through the gas and dust that fills interstellar space without significant absorption. Cocconi and Morrison calculated that existing radio telescopes could detect signals from transmitters similar to the most powerful ones on Earth, if those transmitters were located at nearby stars. The technology for interstellar communication already existed. All that remained was to listen. They proposed focusing on the 1420 MHz hydrogen line, the same frequency that would later make the WOW signal so intriguing. Any civilization that had developed radio astronomy would know about hydrogen emission. It was a natural meeting point, a frequency that every technological species would have reason to monitor. The following year, a young astronomer named Frank Drake conducted the first modern SETI experiment without knowing about Cocconi and Morrison's paper, until his project was already planned. Using the 85-foot radio telescope at Green Bank, West Virginia, Drake observed two nearby sun-like stars, Tau Ceti and Epsilon Eridani, for a total of about 150 hours. He called the project OSMA, after the princess in L. Frank Baum's Oz books, a ruler of a distant land populated by strange beings. Project Ozma detected no alien signals, but it established the methodology that subsequent searches would follow. Point a radio telescope at promising targets. Listen at frequencies where intelligent beings might transmit. Look for signals that stand out from the natural background. Drake went on to become a central figure in SETI, convening the first scientific meeting on the subject in 1961 and developing the Drake equation, a framework for estimating the number of communicative civilizations in the galaxy. The Drake equation isn't really an equation in the mathematical sense. It's a way of organizing our ignorance, breaking the question of how many civilizations exist into a series of smaller questions. How many stars form in the galaxy each year? What fraction of those stars have planets? What fraction of planets are suitable for life? On what fraction of suitable planets does life actually arise? On what fraction of those does intelligence evolve? What fraction of intelligent species develop technology capable of interstellar communication? And how long do such civilizations last? Multiply all these factors together, and you get an estimate of how many civilizations might be out there right now, trying to communicate. The problem is that we don't know most of these factors with any precision. The first few terms have become increasingly well-constrained as we've discovered thousands of exoplanets and learned that rocky worlds in habitable zones are common. But the biological and sociological terms remain almost completely unknown. We have exactly one example of life arising on a planet, exactly one example of intelligence evolving, exactly one example of a technological civilization. Generalizing from a sample size of one is statistically meaningless. SETI proceeded anyway, driven by the recognition that the question was too important to ignore, even if we couldn't predict the answer. Throughout the 1960s, 1970s, and 1980s, various SETI projects operated at observatories around the world. Most were small efforts, using limited telescope time and primitive by modern standards. The Soviet Union conducted extensive searches, sometimes covering more sky than American projects. None detected artificial signals, but the searches were shallow, examining only small portions of the vast parameter space where signals might exist. The lack of detections was unsurprising given the limited sensitivity and coverage. Searching for alien signals was like looking for a needle in a haystack, except the haystack was the size of the galaxy and the needle might not exist at all. NASA entered the SETI field in the 1970s, developing plans for a systematic search far more comprehensive than anything previously attempted. The project went through several name changes as political sensitivities shifted, eventually becoming the High-Resolution Microwave Survey. It was designed to search in two complementary modes, an all-sky survey that would scan the entire sky visible from the northern and southern hemispheres, and a targeted search that would examine about 1,000 nearby sun-like stars with much greater sensitivity. The targeted search would use the world's largest radio telescopes, including the 1,000-foot dish at Arecibo in Puerto Rico. The project represented the most ambitious SETI effort ever conceived, with the potential to detect signals far weaker than any previous search could have found. NASA's SETI project began observations in October 1992, on the 500th anniversary of Columbus's arrival in the Americas. The symbolism was intentional, framing the search as a voyage of exploration into the unknown. But the voyage was cut short. Less than a year later, Congress terminated funding for NASA's SETI program. The cancellation resulted from political opposition rather than scientific failure. Senator Richard Bryan of Nevada led the effort to eliminate the program, arguing that the money would be better spent on other priorities. The scientific community was dismayed, but not entirely surprised. SETI had always been politically vulnerable, an easy target for legislators who could mock the search for little green men and claim credit for cutting wasteful spending. The public relations challenge of SETI was that the search might continue indefinitely without finding anything, making it appear fruitless, even if the lack of detection was simply due to the vastness of the search space. NASA officially withdrew from SETI and has never resumed large-scale search activities, though the agency has recently begun funding research into technosignatures more broadly. The termination of NASA's program could have ended SETI in the United States, but private funding stepped in to fill the gap. The SETI Institute, a non-profit organization founded in 1984, took over the targeted search component under the name Project Phoenix. Using donated funds and telescope time, Project Phoenix observed about 800 nearby star systems over the following decade. The search detected no artificial signals, but it demonstrated that SETI could continue without government support. The SETI Institute went on to develop the Allen Telescope Array, a facility in Northern California designed specifically for SETI observations. Named after Paul Allen, the Microsoft co-founder who provided major funding, the array was originally planned to include 350 small radio dishes that would work together as a single large telescope. Budget constraints limited the initial construction to 42 dishes, but the array has operated since 2007, conducting both SETI observations and conventional radio astronomy research. The most significant development in modern SETI came in 2015, when Russian billionaire Yuri Milner announced Breakthrough Listen, a 10-year initiative with funding of $100 million. Breakthrough Listen represents the largest and most comprehensive SETI program in history. It uses some of the world's most powerful radio telescopes, including the Green Bank Telescope in West Virginia, the Parker's Observatory in Australia, and the Meerkat Array in South Africa. The project has also expanded into optical SETI, searching for laser pulses that advanced civilizations might use for communication. The scale of Breakthrough Listen dwarfs all previous efforts. The program will observe 1 million nearby stars, scan the entire galactic plane, and examine 100 nearby galaxies. The data processing requirements are enormous, analyzing billions of frequency channels simultaneously to search for signals that stand out from the noise. The sophistication of SETI analysis has advanced dramatically since Frank Drake pointed a telescope at Tau Ceti. Modern searches use machine learning algorithms to identify candidate signals, filtering through mountains of data to find patterns that might indicate artificial origin. The Allen Telescope Array can observe multiple targets simultaneously, increasing the efficiency of the search. New techniques look for signals that previous searches would have missed, including broadband signals, signals that drift in frequency, and signals that appear only intermittently. SETI has also expanded beyond radio waves to include optical and infrared searches, gamma-ray analysis, and even searches for physical artifacts in our own solar system. The field has become professionally respectable in a way it wasn't a generation ago. With dedicated researchers, peer-reviewed publications, and institutional support. What would a detection look like? SETI scientists have developed protocols for handling a potential signal, recognizing that such a discovery would be among the most significant in human history and would need to be communicated carefully. The first step is verification. A candidate signal must be observed by multiple independent telescopes to rule out local interference or equipment malfunction. The signal must show characteristics consistent with an extraterrestrial origin, such as movement with the stars rather than with Earth's rotation. Once a signal passes these initial tests, the astronomical community would be alerted, and observatories around the world would turn their attention to the source. International guidelines recommend that no response be sent to an alien signal without extensive consultation among governments and scientific organizations. The implications of contact would affect all humanity, and the decision of whether and how to respond should not be made unilaterally. The closest SETI has come to detection remains the WOW signal of 1977. Nothing since has matched its characteristics or generated the same level of scientific interest. Breakthrough Listen and other modern searches have detected many candidate signals, but all have been traced to terrestrial interference or natural phenomena upon further investigation. The BLC-1 candidate in 2020 attracted significant attention when a narrowband signal was detected from the direction of Proxima Centauri, the nearest star to the Sun. The signal had characteristics consistent with a technological source, including a frequency that drifted in a way suggestive of a transmitter on a rotating planet. But detailed analysis revealed that BLC-1 was almost certainly interference from human technology, probably from equipment on Earth that had been detected through a side lobe of the telescope's beam. The signal matched patterns of terrestrial interference too closely to be credibly extraterrestrial. Each false alarm teaches the SETI community something about the challenges of the search. Radio frequency interference is increasingly problematic as human technology proliferates. Satellites, cell phones, Wi-Fi networks, and countless other devices flood the radio spectrum with signals that can mimic the characteristics SETI is looking for. Even microwave ovens in observatory kitchens can create confusing signals, as the Paraton episode demonstrated. Distinguishing a genuine extraterrestrial transmission from the ever-growing background of human radio noise requires increasingly sophisticated techniques. Some researchers have proposed moving SETI operations to the far side of the Moon, where the lunar bulk would shield the telescope from Earth's radio emissions, creating a quiet zone for listening to the cosmos. The absence of detected signals after 60 years of searching is itself a kind of data. The Fermi paradox asks why, if intelligent civilizations are common in the galaxy, we haven't encountered evidence of them. SETI's null results contribute to this puzzle. We haven't received a clearly artificial signal despite examining hundreds of thousands of stars. Either civilizations are rare, or they don't broadcast signals we can detect, or they avoid contact with emerging species like us, or some other explanation accounts for the silence. Each possibility has implications for humanity's future and our place in the cosmos. Perhaps the universe is teeming with intelligence that we simply lack the ability or knowledge to perceive. Perhaps civilizations routinely destroy themselves before becoming spacefaring, a sobering possibility in an age of nuclear weapons and climate change. Perhaps we are genuinely alone, the only minds in a vast and indifferent universe. The question remains open, and SETI continues to listen, hoping that the next signal to arrive might be the one that changes everything. The summer of 1950 was a time of atomic anxiety and flying saucer fascination. Reports of unidentified objects in the sky had been making headlines for 3 years, ever since pilot Kenneth Arnold described 9 unusual objects near Mount Rainier that he said moved like saucers skipping across water. The term flying saucer entered the language, and the American public became captivated by the possibility that Earth was being visited by beings from other worlds. Against this backdrop, a group of physicists at Los Alamos National Laboratory were walking to lunch one day when their conversation turned to a recent New Yorker cartoon depicting aliens emerging from a flying saucer carrying stolen trash cans. The cartoon was a joke about a rash of missing public trash cans in New York City, blaming the disappearances on extraterrestrials. The physicists laughed about the cartoon as they made their way to the cafeteria. Then, as they sat down to eat, Enrico Fermi suddenly asked a question that would haunt scientists for generations. Where is everybody? Fermi was not an ordinary physicist. He had won the Nobel Prize in 1938 for his work on induced radioactivity and had led the team that built the first nuclear reactor in 1942. His colleagues knew him for his ability to make quick, accurate estimates of physical quantities using rough calculations that nonetheless captured the essential truth of a problem. These back-of-the-envelope estimates became known as Fermi problems, and his question about extraterrestrial civilizations was posed in the same spirit. Fermi quickly reasoned through the implications. The galaxy is about 100,000 light-years across and contains hundreds of billions of stars. Many of those stars are older than the Sun, some by billions of years. If intelligent life arises with any reasonable probability, civilizations should have emerged long before ours. Even with propulsion technology only modestly more advanced than what we can currently imagine, a civilization could colonize the entire galaxy in a few million years. A few million years sounds like a long time, but it's a tiny fraction of the galaxy's age. The galaxy should have been colonized many times over by now. So where are the colonizers? Where are the signals? Where is everybody? The question became known as the Fermi paradox, though Fermi himself apparently didn't consider it particularly paradoxical. He seemed to conclude, at least tentatively, that the answer was probably that interstellar travel was harder than it appeared, or that civilizations didn't last long enough to spread across the galaxy. But the question took on a life of its own, becoming one of the most debated topics in astrobiology and SETI. The paradox isn't that we haven't found aliens yet. The paradox is the apparent conflict between the high probability that alien civilizations should exist and the complete absence of evidence that they do. Every proposed solution to the Fermi paradox carries profound implications for humanity's future. Some solutions are optimistic, suggesting that we simply haven't looked hard enough or that contact is coming soon. Others are deeply pessimistic, implying that civilizations routinely destroy themselves or are destroyed by external forces. Understanding why the universe appears empty might be the most important question our species ever confronts. Let's examine the numbers more carefully. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Recent discoveries of exoplanets have shown that planetary systems are common, perhaps nearly universal. The Kepler mission alone identified thousands of planets, and statistical extrapolation suggests that there are more planets in our galaxy than stars. Many of these planets orbit in the habitable zones of their stars, where temperatures allow liquid water to exist on the surface. Conservative estimates suggest at least 10 billion Earth-like planets in habitable zones exist in our galaxy alone. Even if the probability of life arising on a suitable planet is extremely small, the numbers are so vast that life should be common. And if life is common, intelligence might be common too. Evolution on Earth produced intelligence at least once, and convergent evolution suggests that similar solutions to biological problems arise independently on different lineages. Eyes have evolved dozens of times independently. Flight has evolved multiple times. Perhaps intelligence is also a convergent feature, likely to arise whenever the conditions are right. The time factor makes the paradox more acute. The Sun is about 4.6 billion years old, but the galaxy is about 13 billion years old. Stars and planets formed billions of years before our solar system coalesced from its primordial cloud. If life arose on some of those earlier planets and evolved intelligence at a similar rate to Earth, civilizations could have emerged billions of years before humans existed. What would a civilization billions of years old look like? We can barely imagine what human technology will be like in 1,000 years, let alone a billion. Such ancient civilizations would have had time to develop capabilities that would seem like magic to us. They would have had time to colonize not just the galaxy, but perhaps multiple galaxies. The Fermi paradox asks why, with such a head start, at least one civilization hasn't spread across the cosmos in a way that would be obvious to us. The possible solutions to the Fermi paradox fall into several broad categories. The first category suggests that we're essentially alone, that intelligent civilizations are far rarer than the optimistic estimates imply. This is sometimes called the rare Earth hypothesis, after a book by Peter Ward and Donald Brownlee that argued Earth might be exceptionally unusual in ways that made complex life possible. The Moon stabilizes Earth's axial tilt, preventing wild climate swings that might otherwise make evolution of complex life impossible. Jupiter acts as a gravitational shield, deflecting comets and asteroids that would otherwise bombard Earth more frequently. Plate tectonics recycles carbon and regulates the climate over geological timescales. The Sun is unusually stable compared to many stars. Perhaps the combination of factors that made Earth suitable for intelligent life is extraordinarily rare. So rare that we might be the only technological civilization in the galaxy, or even the observable universe. Related to this is the concept of the Great Filter, proposed by economist Robin Hanson. The Great Filter is the idea that somewhere between dead matter and galaxy-spanning civilization, there's an extremely improbable step that almost never succeeds. Life might be that step, arising so rarely that Earth is the only example in the galaxy. Or the transition from simple cells to complex cells might be the filter. This transition happened only once on Earth, despite simple cells existing for over 1 billion years first. Or the evolution of intelligence might be the filter. Or the development of technology, or the transition to a spacefaring civilization. The unsettling question is whether the Great Filter lies behind us or ahead of us. If it's behind us, if the improbable step was the origin of life or the evolution of intelligence, then we've already passed the filter and our future is relatively open. But if the Great Filter lies ahead, If civilizations routinely destroy themselves or are destroyed by some unknown catastrophe after reaching approximately our level of development, then we face the same fate. The silence of the galaxy might be a warning that almost no one survives to colonize the stars. The second category of solutions suggests that civilizations exist, but we can't detect them. Perhaps they don't use radio waves for communication, having moved on to technologies we haven't invented yet. Our radio searches might be like indigenous people watching for smoke signals while jets fly overhead. Perhaps civilizations go through a brief window of using radio technology before advancing to something else, and we've missed the signals from everyone who passed through that window before us. Perhaps they communicate by methods we wouldn't recognize as signals at all, using phenomena we haven't discovered or encoding information in ways we can't decode. The universe might be humming with alien communications that we simply lack the ability to perceive. Another version of this hypothesis suggests that civilizations turn inward rather than outward. Why colonize the physical galaxy, with all its difficulties and dangers, when you can create virtual realities of unlimited scope within computer systems? A civilization with sufficient computing power could simulate entire universes, exploring simulated stars and planets without ever leaving home. The pleasures and adventures of virtual existence might far exceed anything the physical universe offers. Perhaps advanced civilizations retreat into their computers, becoming invisible to outsiders while experiencing subjective eons of rich existence within their simulations. From outside, their star systems might appear dead, their worlds silent, while inside, quadrillions of minds live lives we can barely imagine. The third category proposes that civilizations exist and are detectable, but choose not to be detected. The zoo hypothesis suggests that alien civilizations are aware of us and deliberately avoid contact, treating Earth as a nature preserve to be observed but not disturbed. Perhaps there's a galactic protocol, an agreement among established civilizations to leave emerging species alone until they reach some threshold of development. We might be surrounded by watchers who will reveal themselves when we're ready, or never, depending on how we develop. The quarantine hypothesis is a darker version, suggesting that we're avoided not out of respect, but out of caution. Perhaps civilizations have learned that contact between species at different technological levels leads to catastrophe, and they keep their distance for their own protection or ours. The Berserker hypothesis proposes an even grimmer scenario. Perhaps the galaxy is dangerous, patrolled by automated weapons that destroy any civilization that reveals itself. The silence wouldn't indicate an absence of civilizations, but would be the survival strategy of civilizations smart enough to stay quiet. Anyone who broadcasts their presence is eliminated. The survivors are those who hide. If this hypothesis is correct, our own radio emissions over the past century have been a terrible mistake, announcing our existence to potential predators. The Berserker hypothesis is troubling because self-replicating weapons, once launched, could persist long after their creators are gone. The galaxy might be haunted by ancient killing machines from a war fought billions of years ago, still hunting for new targets. A more speculative category of solutions questions our assumptions about what civilizations would do. The assumption that advanced species would colonize the galaxy comes from extrapolating human behavior. But alien minds might not think like human minds. Perhaps most intelligent species don't have the drives that lead to expansion and colonization. Perhaps they're content to remain on their home worlds, living sustainable lives for millions of years without ever developing the desire to spread across the stars. Perhaps the very traits that lead to technological development also lead to self-destruction, so that no species with our pattern of restless ambition survives long enough to colonize widely. Perhaps intelligence takes forms that don't build radio transmitters or spacecraft, like whales and dolphins on Earth, who are highly intelligent but will never send signals into space. The Fermi paradox remains unresolved because we have so little data to work with. We have examined only a tiny fraction of the stars in the galaxy with SETI searches. We have been listening for less than a century, an instant in cosmic terms. We have been capable of detecting most types of potential signals for only a few decades. The absence of a detection so far might simply mean we haven't looked long enough or hard enough. But the absence does carry some information. We can say with increasing confidence that there are no civilizations within a few hundred light years of Earth that are continuously broadcasting powerful signals in our direction at the frequencies we've monitored. The local neighborhood appears quiet, even if we can't say anything definitive about the rest of the galaxy. The philosophical implications of the possible answers are profound. If we're alone, if the great filter lies behind us, and we are the only technological civilization in the galaxy, then we carry an extraordinary responsibility. Everything that intelligence might accomplish, everything that consciousness might experience, depends on our survival and flourishing. The universe has produced minds capable of understanding it, and those minds exist only here, on this small planet, in this moment. The weight of that possibility is staggering. We would be not just rare but unique, the only chance for the universe to know itself. Every species we drive to extinction, every ecosystem we destroy, every existential risk we fail to mitigate, takes on cosmic significance. We would be the custodians of something precious beyond measure. If civilizations are common but short-lived, if the great filter lies ahead of us, then the Fermi paradox is a warning we must heed. Something destroys civilizations after they reach approximately our level of technology. Nuclear weapons, engineered pandemics, artificial intelligence, climate change, or some threat we haven't yet encountered might be the instrument of our destruction as it has been for countless others before us. The silence of the galaxy would be the silence of graveyards, worlds that once held promise but succumbed to dangers they couldn't navigate. Our task would be to understand what kills civilizations and avoid that fate, to be the exception rather than the rule, to break through the filter where so many others have failed. If civilizations exist but hide, then we exist within a community we don't yet perceive. The silence might end suddenly, shockingly, when they choose to reveal themselves, or the silence might be permanent. Our species perpetually excluded from whatever galactic society exists beyond our awareness. We would be like isolated tribes, unaware of the wider world, except the isolation might be enforced rather than accidental. What would it mean to live in a universe where we're deliberately ignored? What would it mean to discover that the silence has been a choice rather than an absence? These questions can't be answered from our armchairs. They require continued searching, continued listening, continued exploration. Every new star system examined, every new frequency monitored, every new method developed brings us closer to an answer. SETI might succeed tomorrow, or might never succeed, but the attempt is justified by the importance of the question. The Fermi paradox will be resolved eventually, whether by detecting signals, by finding evidence of past civilizations, by confirming that we're alone, or by being contacted by others who have been watching all along. Until then, the great silence of the universe poses questions that go to the heart of what we are and what we might become. We have traveled a long road together through this exploration. We began with Carl Jansky's accidental discovery of radio waves from space, a young engineer trying to track down sources of telephone static, who instead opened humanity's ears to the cosmos. We followed Jocelyn Bell's detection of impossibly regular pulses that briefly seemed like messages from alien intelligence before revealing themselves as the spinning corpses of dead stars. We examined the WOW signal, 72 seconds of narrowband radiation that matched every prediction for an extraterrestrial transmission and then vanished forever, leaving decades of frustration in its wake. We explored fast radio bursts, millisecond flashes from across the universe that puzzled astronomers for years before being traced to the violent outbursts of magnetars. We wandered through the strange behaviors of pulsars, their glitches and nulls and mode switches that reveal how much we still don't understand about matter under extreme conditions. We visited Tabby's star, where the alien megastructure hypothesis captured the world's imagination before succumbing to the mundane reality of circumstellar dust. We examined mysteries from our own solar system, from Saturn's misleading radio emissions to the unexplained acceleration of an interstellar visitor. We surveyed 60 years of deliberate searching for intelligent signals that has so far returned only silence. And we confronted the Fermi paradox, The troubling question of why, in a galaxy that should be teeming with life, we appear to be alone. What does all of this mean? What have we learned from decades of strange signals and unexplained anomalies? The most important lesson might be humility. Again and again, signals have arrived that seemed to defy explanation, that appeared to require exotic physics or even intelligent design. Again and again, patient investigation has revealed natural causes, but those causes have been stranger than anyone anticipated. Pulsars were not little green men, but rotating neutron stars, objects so dense that a teaspoon of their material would weigh billions of tons. Quasars were not inexplicable point sources, but supermassive black holes, devouring matter at the centers of distant galaxies. Fast radio bursts were not cosmic mysteries beyond comprehension, but magnetars experiencing violent magnetic rearrangements. The universe has consistently proven more imaginative than human scientists, producing phenomena that strain our ability to conceive, but ultimately fit within the framework of natural law. This pattern suggests caution about both premature excitement and premature dismissal. When a strange signal arrives, the temptation is to leap to the most dramatic interpretation, to see aliens behind every anomaly. The WOW signal, Tabby's star, and Oumuamua all generated tremendous public excitement, precisely because they seemed to offer evidence of extraterrestrial intelligence. But the history of astronomy shows that natural explanations, however exotic, have always prevailed. At the same time, the history shows that strange signals should not be dismissed without investigation. Every case that seemed to point toward aliens actually pointed towards something scientifically valuable. Pulsars revolutionized our understanding of stellar evolution and provided tools for testing general relativity. Fast radio bursts are now being used to probe the intergalactic medium and measure the distribution of matter in the universe. The investigation of anomalies drives discovery, even when the anomalies turn out to have prosaic causes. Another lesson concerns the importance of patient, systematic observation. The WOW signal remains unexplained in part because it was a single event that never repeated. Fast radio bursts remained controversial for years because early detections were sparse and couldn't be verified. The breakthrough in understanding FRBs came when repeating sources were discovered, allowing astronomers to accumulate data and localize the sources precisely. Science progresses through reproducibility, through the ability to return to a phenomenon and study it repeatedly. Singular events, no matter how dramatic, provide limited information. The universe is under no obligation to repeat its performances for our convenience, but when it does repeat, understanding follows. The technological dimension of this story deserves recognition. Every advance in our ability to detect strange signals has come from engineering progress. Radio astronomy itself became possible only when radio technology matured enough to build sensitive receivers and large antennas. The detection of gamma-ray bursts required satellites above Earth's absorbing atmosphere. The localization of fast radio bursts required interferometric arrays that could pinpoint sources with arc-second precision. The next generation of discoveries will come from instruments now being built or planned. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the largest radio telescope ever built, with sensitivity far exceeding any existing instrument. The Vera Rubin Observatory will survey the entire visible sky repeatedly, finding transient objects like Oumuamua that would previously have gone unnoticed. Space-based gravitational wave detectors will open entirely new windows on the universe, detecting signals that no electromagnetic telescope can see. The strange signals of the future will be captured by technologies we're only beginning to develop. The human element in this story is equally important. Behind every detection is a person who noticed something unusual and had the curiosity to pursue it. Jocelyn Bell could easily have dismissed her bit of scruff as interference. Jerry Amon could have glanced at the printout and moved on. Duncan Lorimer could have ignored the anomalous burst in archival data that everyone else had overlooked. Science advances because individuals pay attention, ask questions, and refuse to accept easy explanations. The volunteers who flagged Tabby's star in the Planet Hunters project were not professional astronomers, but curious citizens who wanted to contribute to the search for knowledge. The SETI enterprise has always drawn on amateur enthusiasm alongside professional expertise, recognizing that the search for extraterrestrial intelligence belongs to all humanity, not just specialists. The question of extraterrestrial intelligence remains open. After 60 years of searching, we have found no confirmed signals of artificial origin. The WOW signal remains intriguing, but unverified. Every other candidate has been explained as natural phenomena or terrestrial interference. The Fermi paradox poses its uncomfortable questions, and we have no definitive answers. But absence of evidence is not evidence of absence, particularly when the search has covered only a tiny fraction of the possibilities. The galaxy contains hundreds of billions of stars. We have examined thousands in detail. Signals might be rare, intermittent, directional, or encoded in ways we haven't thought to look for. The next signal could arrive tomorrow, or we might search for centuries without success. Either outcome would teach us something profound about our place in the universe. If signals from extraterrestrial intelligence are eventually detected, the implications would be transformative in ways we can barely anticipate. The confirmation that we're not alone, that intelligence has arisen elsewhere in the cosmos, would force a reassessment of everything we believe about ourselves and our significance. Religious traditions would need to accommodate the existence of other thinking beings. Philosophical questions about consciousness and meaning would take on new dimensions. The details of any detected signal, whether it contained information we could decode or remained frustratingly opaque, would occupy scientists and humanists for generations. Even a signal that told us nothing about its senders beyond the fact of their existence would change humanity's self-understanding forever. If no signals are ever detected, if the silence persists despite increasingly comprehensive searches, that too would carry meaning. It would suggest that intelligence is rare, that the conditions for its emergence are stringent beyond our current understanding. It might indicate that we bear unique responsibilities, that the continuation of conscious experience in the universe depends on what we do with our moment in cosmic history. The silence would be an answer, even if not the one we hoped for. And it would leave open the possibility that we might become the civilization others search for, that our signals might someday reach beings wondering whether they're alone, that we might be the ones to break someone else's silence. The strange signals we've explored in this journey have all contributed to our understanding of the cosmos. They've revealed neutron stars and black holes, magnetars and intergalactic plasma. They've tested our instruments and our theories, pushed us to develop new technologies and new explanations. They've engaged the public imagination in ways that routine discoveries rarely do, reminding us that the universe remains full of mysteries and surprises. The search for strange signals is not separate from the rest of astronomy, but central to it. Anomalies drive progress. Unexplained phenomena demand explanation. The history of science is a history of puzzles solved and deeper puzzles uncovered. We live at a remarkable moment in that history. Our species has existed for perhaps 300,000 years, but we've been able to detect signals from space for less than a century. Our radio telescopes have been sensitive enough to search for extraterrestrial intelligence for only a few decades. The window of time during which we've been listening is a blink of an eye compared to the age of the galaxy. We're at the very beginning of the search, with most of the work still ahead of us. The strange signals that have arrived so far are only the first whispers of what the cosmos might eventually tell us. Future generations will have instruments we can't imagine. We'll search portions of the universe we can't yet reach. We'll ask questions we haven't thought to ask. Right now, as you finish this exploration, signals are traveling through space toward Earth. Some are natural. The radio hum of pulsars, the flickering of active galaxies, the cosmic microwave background radiation that has been traveling since the universe was young. Some might be artificial, messages from civilizations we know nothing about, beacons waiting to be noticed. They're passing through your body as you sit here, undetected and unacknowledged, carrying information we might never decipher. The universe is speaking in countless voices, and we've only just begun to listen. The strange signals that have arrived so far have taught us that the cosmos is stranger than we imagined, and that our imagination must continually expand to encompass what we find. Keep looking up, keep asking questions, keep wondering about what might be out there, waiting to be discovered. The search for strange signals is ultimately a search for meaning, for our place in a universe vast beyond comprehension. Whether we find companions among the stars or confirm our solitude, the search itself ennobles us. It expresses what is best in our species: curiosity, persistence, the refusal to accept ignorance as permanent. The signals are out there, natural and perhaps artificial, waiting for someone to notice them. The next great discovery might come from a professional astronomer analyzing data from a billion-dollar telescope, or from an amateur enthusiast noticing something odd in publicly available archives. It might come tomorrow or in 100 years, but it will come, because the universe is generous with its mysteries, and human beings are relentless in pursuing them. The cosmic whispers continue. Pulsars spin and flash. Magnetars burst with unimaginable energy. Somewhere, perhaps, minds we've never met contemplate their own skies and wonder whether anyone is listening. The conversation between humanity and the cosmos has only begun. What we've learned so far is prologue to discoveries yet to come. The strangest signals ever received from space might not be strange at all compared to what awaits us, and that thought, that certainty of wonders yet unknown, is perhaps the greatest gift that the cosmos offers to those who pay attention. The universe is speaking, we are listening, and the story is far from over.